N.S. Sathyamurthy Award way back in 2001, Ravi Kumar Bhalla Award, and Certificate of Appreciation from Rotary Club of Pune, Rotary International. And with this brief introduction and the fact that he is the spokesperson of LIGO India and member secretary of LIGO India Scientific Management Board, uh, I would like to extend a very warm welcome to Professor Tarun Sauradip and request him to deliver the first foundation day lecture today. Professor Sauradip.
Thank you, Topo, for the very generous introduction. I should begin by thanking IOP for giving me this opportunity to be part of your 47th Foundation Day celebrations. It's always a pleasure to associate with IOP. I have had many visits over my career, and not very recently though, and no one has been traveling recently, so I guess I am looking forward to visiting again soon. So I wanted to basically give you an overview of what's happening in the country. I mean, the emphasis is more on, trying to open up new horizons of frontier research in India. And that has been something that I've been personally very vested for more than a decade now. And so I'll be talking about mainly about the LIGO India project, which is currently underway, and in terms of construction, and also briefly mention some futuristic proposal that we hope ISRO will, buy into sometime in the near future. Okay, so the whole bit, but the connecting thread is gravitational waves. Okay, and I wanted to say why gravitational waves are important. So, at IOPB, of course, there are researchers looking at all kinds of interactions. It's always a big breakthrough in science when you start, kind of probing nature with a new interaction. And gravitation, of course, we have seen gravity in action in many ways for centuries now, but we have understood it. But we have never seen the radiative modes of gravitation, and so that's a big change. So let me begin by just a very brief thing of Einstein's gravitation. I was thinking that there were many students. So anyway, so this is slightly laymanish for the August audience we have, but please bear with me. So the gravitational waves come naturally out of Einstein's gravitation, and because there we understand gravitation not as a force, but as curvature of space-time determined by the matter content. So the matter tells space-time how to curve, and space-time tells matter how to move. The famous lines of Wheeler. And so if you have matter in motion, just like if you stir up the surface of a lake, you create ripples. So same here, if you stir up the space-time fabric with massive bodies moving around, or any body moving around, any masses moving around, you create ripples. And that is the mode by which gravity talks. I mean, just like light talks through, electromagnetism talks through light, or photons. We have gravitational waves as the mediator, the propagator in this. In GR, it's very similar to electromagnetic waves. The gravitational waves actually are believed to travel at the speed of light in Einstein's gravity. And they have been confirmed to a very, very high accuracy with the recent gravitational wave observations. These are transverse, and that's also, there are serious limits on it, on non-transverse or longitudinal modes. And they have two states of polarization. This is the default Einstein's gravity prediction. And these states of polarization are slightly different from electromagnetism in the sense that these are spin-2 fields. So they are basically shear fields. So have, two polarizations that actually are 90 degrees apart spatially in the plane perpendicular to the propagation direction. But what is very important to realize is why are gravitational waves such a big deal? As I said, I mean, the main point is it's a major qualitatively unique prediction beyond Newton gravity. You could think of Einstein's gravity, in the static cases or slow moving cases as corrections to Newton's gravity. But, Newton's gravity cannot accommodate gravitational waves. It doesn't have propagating modes. And now that we have measured directly gravitational waves, that's a really, really big cornerstone in progress of science. And so this is just a visual picture of what's happening. So you have two neutron stars shown here, churning up the fabric of space. Oh, sorry. I think. Yeah, so you have neutron stars churning up space, and this is exactly how, just like ripples on the surface of a lake, you can see the gravitational waves are ripples in curvature that move out, and then because we are far away detecting it. So what happened with the first detection? So if you were in the galaxy where the first detection happened, this is a galaxy far, far away, and billion light years away. So this happened a long time back. And in that galaxy, the Milky Way of or the stars would look like this because they'll be pocked by these two black holes. And the whole warping that you see in the stellar pattern out there is because of the extreme, gravitational field of these black
Professor
holes. You can
Sauradeep.
see that there's
Hello, Professor
yeah.
Sauradeep. We are not able to see your
Hello.
slides.
Yeah. Somehow it has gone missing. Yeah.
Oh, you can't see my slides?
Just
Okay,
just
I
the
see.
last one. Just the last one, I think.
Yeah. This has got disappeared.
Okay. Just give me a minute.
Yeah. Please start sharing. Take your time, please.
Okay, can you see it now?
Yes, it is coming up. Yes, now we are.
Yeah. On you are at the first slide. Yeah.
Yeah. Okay, excellent. Okay, great. Okay, so yeah, so here, so two black holes, of course, next to each other, if they have any relative velocity, they would kind of, spin around each other and, as you know, merge. And you can see how, due to the changing pattern of the stellar background, you can see how the gravitational field around it is getting dynamic and, essentially churning up. So not only do you have gravitational potential, but you have, momentum of space-time, which is being affected, and then that is carried out as gravitational waves. So this is the merger picture that I'm sure you have all seen. Again, I think, did I lose you?
Yes, we are not able to see the slides again.
Okay, so this is...
Yeah, it has come back. Tarun, I have a kind suggestion. Maybe for some time, for few slides at least, you may continue with this normal view rather than full screen mode. I don't know. I mean, just suggesting because you will be utterly disturbed if it keeps happening.
No. So I know this is happening because of, whenever I try to start a video, this is my cursor.
Please go ahead.
Actually, yeah. So it's a
Okay.
problem. I know what is happening. Okay, great. So let me go ahead and say that these were first detected on September 14, 2015 Of course, the announcement was made the next year, on February 11th, 2016. And what was announced is the merger of two black holes, seen as these two traces that you see here. Are you with me?
Yeah, we are able to see you. See your
You're able
slides.
to see me? Okay. I'm.
Yeah, it's okay.
Okay, so then these are the two traces seen at the two detectors, gravitational wave detectors in the US. And you can see that they were consistent, only some 7 milliseconds apart. And then essentially that sort of narrated a story which gave us really what is called the discovery of the century. So it was the first direct detection of gravitational waves. It was also the direct detection of a black hole, right? And in the sense that there was signals at the end of the merger which were consistent with the black hole settling down, although that was not confirmed at high significance, but that was an important aspect. And astrophysically, this was also the first detection of a black hole binary system, direct detection, right? So I should mention the Indian story associated with this. So this fact that we have a detection of a black hole comes from the ring down. So you can see after the merger where the peak amplitude is, there's a phase which actually is modeled by a pure note, a pure note which is damped. So it's like a bell, ringing of a bell. So that's, something that ring down is something that Professor Vishweshwara, who has been a relativist in India, passed away a couple of years back, actually predicted as a young researcher in Maryland, okay, and this Nature paper. And in the gravitational wave field, Sanjeev Dhurandhar and Satya Prakash had laid some of the foundational work on data analysis in the 1990s. And Bala Iyer, so there were two groups in India which have been working on gravitational waves. So Bala Iyer had been working on the source modeling with the French group of Luc Blanchet. And early. So we have a history of gravitational waves work. And so we are onto this game now of studying physics at the extreme. Now, why do I call these mergers physics at the extreme? Because if you were, thinking about the first merger, you realize that there was a 30 solar mass black hole which collided with a 40 solar mass black hole. And as you know, for each solar mass, you basically take a kilometer kind of scale. So the first one is 30 kilometers in radius, but packs the amount of matter which is equivalent to packs mass equivalent to 30 solar masses. And so these are extremely heavy bodies. And they merged and formed this massive 70 solar mass, 61 solar mass black hole. Okay. And so these are terrestrial sized object, but extremely massive. And for particle theorists, it would be interesting. So you obviously, in LHC, collide protons, which are, uh, massive than electrons, and then they collide with each other and the substructure comes out. So here you have these black holes, close to their merger. The relative velocity, if you see it, the plot here, was started with 0.3 c and then went up to past the half the speed of light. So imagine these extremely massive bodies colliding with each other almost at the speed of light, right? So these are collider events happening with massive particles in the universe. Okay, and the physics at the most extreme scales are kind of revealed through these collisions. And the energetics of this is very interesting. So three solar masses, of was converted to gravitational wave energy in 0.2 seconds. So if you convert to watts, it's like 10 to the 49 watts. So it's more energetic than any electromagnetic phenomena ever seen. And the luminosity, if you compare it to the electromagnetic emission of all the stars in the universe, it would be higher than that, right? So every event of this is an extremely energetic event, and hence we kind of get a glimpse into physics of the extreme, if there is some physics beyond what we know. This is with black holes. Black holes are pure space-time constructs. So, there is no other interaction that can come out of it, in black hole mergers. But there are other compact objects like neutron stars. And neutron stars, when they merge, they not only have very high energetics, they are almost, a few solar mass, 1.5 to 2 solar mass objects colliding with each other, just like the collision that I showed you. But in this collision, there is actually nuclear matter which crashes into each other. And then in those high energy things, there are, a lot of nuclear processes that happen, and very unique processes that actually give you emission that can be seen in electromagnetic telescopes, and these can be identified as our process nucleosynthesis happening. So we had one such event in 2017, which luckily was also spotted by the Swift satellite very soon after the gravity wave event happened. So, and this was then followed up by 70 observatories all across the world, all across the globe. You can see the globe here. The two here in yellow are three in yellow are the gravitational wave observatories, and rest of them in blue are the number of observatories that made follow-up observations. And one of them here is GMRT, and this is probably Hanley. And there were 7 space observatories. So you can see that one single event brought together over 3,000 researchers to kind of study what comes out of a neutron star colliding into another neutron star. So let me first talk about what it gave in terms of astrophysics. So as I said, it gave you the answer to the kind of nuclear processes that happen at the nuclear densities provided by neutron stars. And these were really mapped out across. So this kilonova, decaying neutron-rich material was seen in infrared, and this radio remnant was studied for almost a year afterwards. And then we also got answers to questions like, where are the heavy elements like gold and platinum cooked up in the universe? We knew for a long time that supernovae explosions cannot provide enough of these elements. And it was conjectured that it must be neutron star mergers. And now we have confirmed that very well. This event also opened up another kind of window to cosmology. So as you may have heard recently, there is this Hubble tension, right? So there are these 2 bands. Here, in the cyan one here, you see the measurement from Planck, which is very tight. And in this orange band are measurements from the local universe of the expansion rate of the universe. And these seem to be in tension. Gravitational waves provides an independent measure of the Hubble constant. And there was one such estimate done with this single event. And that can be improved as more events are. And that's a game that gravitational wave cosmologists are playing, trying to measure H0 from gravitational wave events. So these are kind of examples of the kind of physics they're coming. There are lots of other physics, like the test of GR, as I said, the speed of gravitational waves is kind of the same as speed of light up to 1 part in 10 to the 15, which also sets limits on the mass of gravitons. And, so these are fundamental answers that we are getting from these. So my talk does not, I do not want to dwell only on the science that comes out. There's interesting science coming out. And you can see that the observatory is fully engaged. Now, these blue dots here show the merger events of black holes. So every two going up to a third. And then these purple ones are, mergers. No, purple ones are actually electromagnetic black holes known. So you see that gravitational wave already has opened a world into black holes which were unknown. Electromagnetically known black holes were never larger than 20, 25 solar masses. But you can see most of the events that we have detected in LIGO are well over that. In fact, there are more above 25 solar mass than under 25 solar masses. Similarly, we knew of a lot of neutron stars, which are shown in yellow. These are known from electromagnetic observations, the pulsars and things like that. But now these in orange is slowly telling you the number of neutron stars we know from gravitational wave events, right? So you can see that this stellar graveyard is slowly getting filled up, and there are lots of interesting questions that will come up. For example, you can see that electromagnetic black holes and neutron stars, there's a mass gap between 2 solar masses to 5 solar masses. Okay, and one did not expect compact objects in that range. But now with gravitational wave events, there are already some events that sit right in this mass gap. And they raise questions about whether there is actually a mass gap. Similarly, there's an interesting question of how massive a star needs to be to form a black hole. And we used to believe that you cannot form black holes say above something like 100 solar masses. And we have seen already that black holes form of masses, from black holes of close to 100 solar masses, you have black holes as large as 140 solar masses. So this is an interesting, astrophysics as well as, fundamental physics frontier that is opening up. And this is the horizon which will, really be showing us the way in the next decade. Now, what makes all this possible? To make all this possible, you need apparatus that can measure displacements of 2 mirrors placed 4 kilometers away by an extraordinarily small amount, like 10 to like attometer, right? And this presents a big challenge, right? And that is why the first discovery was heralded immediately, next year with a Nobel Prize, and there was a breakthrough prize given to the collaboration, and so the attention was quite justified. And I should also say the fact that we were, we started into this field with LIGO India way back in 2011, allowed us to be a significant partner in these discoveries. So we had about 37 authors from 9 Indian institutions. And now over 100 researchers are part of this collaboration. So how does one measure gravitational waves? So gravitational waves, as I said, are stresses. It's like a stress propagating. So what it does to a ring of particles is it takes the circle and deforms it into an ellipse and back. So if you monitor 3 particles, and you can do that with a laser interferometer, then you can detect the displacement of these 2 mirrors relative to the beam splitter, at a very high precision. You know that interferometry, a Michelson interferometer, is a very nice device for doing such measurements. But here, to get to this 10 to the minus 20 meter kind of regime of displacement that you want to measure, your detector has to be huge. Okay, so it's 4-kilometer long detector. These are LIGO Hanford and LIGO Livingston, which made the first discovery. These are 4-kilometer long Michelson interferometers with Fabry-Perot enhancement of the light. And this is what the detector looks like. I mean, this is what pictures from Hanford show you. So it's a very large scale apparatus with, beam tubes about 1 meter long, in ultra high vacuum. And it has, amazing optics. So the mirrors that we are talking about in terms of which make up the interferometer, mean core optics, are 100 times better in terms of surface specifications than the best telescope optics. And these are fairly large mirrors, 34 centimeters, and you can see that the small. So these kind of things coming into the country has spurred a lot of activities in labs trying to get to these kind of technological capabilities. Okay, these mirrors, for example, are unique. They are, globally unique in the sense that there's one country which can cast it, one lab in one country, one lab in one country, another country that can coat it, polish it, and the third where it's coated. So these are at the top and of technology, and these 40-kilogram mirrors hang by glass fibers which are welded on, and this is done to kind of make sure that the mechanical Q of this mirrors is very high, so that their vibrational modes are isolated from the modes that we want to measure. So these seismic isolation has to be at 12 orders of magnitude, and mechanical isolation. So this is an apparatus that kind of involves technology at the cutting edge. The lasers are also unique. They are continuous lasers with very narrow line width, with frequency stability and intensity stability very high. A narrow, so it's an infrared laser, but sub-kilohertz line width. So it's a very as monochromatic as laser can ever get. And also, currently, the LIGO detectors have just started using squeezed light. So we are, in fact, our measurements, the most recent measurements, involve quantum manipulation of light. And it uses squeezed light injected into the dark port. And these are the kind of quantum technology that have been talked about in the country a lot. Okay, so this has a high potential to draw people into it. So let me get to LIGO India. What is India doing? So in 2011, we proposed to the Mega Science Committee the idea of hosting a detector here, constructing a detector. And there are 4 lead institutes involved in this: RRCAT, IPR, TCSEM, and IOCA. And this was approved by the Union Cabinet in 2016. And now site has been acquired and some construction has already started. Why did we want to build another LIGO? That's because India is the southernmost possibility from the other 2, and also at a large distance from LIGO US. And this provides us a triangulation of sources, which is far, far superior than what currently exists. So at this point, when we see a black hole, we can locate it on the sky in this huge uncertainty region, right? But with LIGO India, this will shrink to very small size. This is with the first detection. I can show you, if someone is interested, what is this situation with the neutron star black hole binary case. So this is the LIGO India project. It's an Indo-US project with LIGO labs on one side and the 4 institutes I talked about in the side. And we are supposed to construct and operate this detector. What comes from US is the key hardware component of an advanced LIGO detector, which are these mirrors, laser, and the isolation thing that we talked about. Okay, but the rest comes from us. And LIGO India is the main science goal is to exploit gravitational wave observations as a part of multi-message astronomy. And the biggest attraction to have such a detector on Indian soil is the high-end frontier technology. It will transform the capabilities in our labs and industry. It will, of course, as I said, it has a geographical advantage, but it also has a demographical advantage. And that is very clear. In these decade, the rate at which our groups are growing in India is not really possible in many countries. We are in a very good situation with a lot of young people and fairly, high level of undergraduate and postgraduate studies, right? And LIGO India touches a whole range of, it's an astronomy project in some sense. We are doing gravitational wave astronomy, but that does tie in with various other astronomy that India is engaged in. But we will be doing fundamental physics, we'll be making precision measurements, but most importantly, we will be pushing the frontiers of so many technologies, the capabilities of so many technologies in the country. So, for example, the vacuum infrastructure, the company which would go and make it ultimately, has to be something which will have, certificate for doing world-class research, because this is 10 million liters of space evacuated, one contiguous vacuum system, and it is evacuated to ultra-high vacuum. Okay, and it requires immense capability to be able to set this up. This is the innards of the vacuum tube that we will set up. In that, there will be extremely complicated optics. This is a much simplified diagram of the optics of this mirrors, showing the central part and these two ends going into the two arms. And the control system that comes with it are things that are going to be, taking, a few notches above what is the current capability here in the country. So what's the status of the project? We identified the site in 2016 formally. After a huge effort, it took 6 years of work to do this. And we looked about 40 sites all over the country, did a lot of seismic measurements and all that. And this Onda is the final site that has been selected. A lot of activities are going on the site. Actually, there are more recent pictures of some buildings that are coming up, which I'm not showing at this time. And we have also started fabricating elements of the vacuum chamber. So here are these vacuum chambers being produced in Bangalore. And you can see, I'll just show you a next picture of these. You'll get an idea of the scale of these two kinds of chambers that have been built. So this is like lifted with cranes and packed and shipped. And they were shipped to off-site LIGO India off-site facility, which has been built in Arakat. And that's where these chambers are now. And these will form, these prototype chambers will be used for off-site training facility that we are creating for LIGO India. And you can see now the scale of this chamber with people standing in front of it. Okay, so it's every bit of it is a very interesting story. So they took about a week for it to get transported from, these trucks from Bangalore to Indore with a lot of anecdotes and stories. So LIGO India is on the way, and this is really exciting. And this window is one of the 4 windows that are expected to open up in gravitational waves. So as I as the title of my talk says, I believe that gravitational waves is the new horizon. It will open up new views into the universe and understanding of nature. So we have opened one window with LIGO. In 2030s, ESA will set up 3 spacecrafts which will exchange lasers between them and form a gravitational wave observatory in space, a laser interferometer space antenna that will measure lower frequency gravitational waves. Then there will be this pulsar timing array, which is already underway, which monitors pulsar timing for extremely low frequency. And then finally, there's another window waiting to open, which is the detection of primordial gravitational waves in the CMB polarization. Many of you will recall a false start we had with announcement by BICEP of detection of this signal, but that turned out to be false, as shown by Planck. But this is technology that is ready to be deployed on a spacecraft. So what is the idea there? In that, actually, you're using the entire universe as a gravitational wave observatory. So remember, you're looking at distortions of mirrors for LIGO. Here, if you imagine, you have a plasma surface from where the cosmic microwave background comes to us, placed 14 gigaparsecs, that's 43 billion light years away. So you can imagine this is exactly the picture you should have, that there's a shell which is surrounding us. And if gravitational waves of cosmological wavelengths are there, they will distort this shell. And, this gravitational wave detector will get distorted due to the presence of gravitational waves, primordial gravitational waves. Of course, this is an extremely exaggerated picture, but this will happen in one part in 10 to the 8, not one part in 10 to the 18. So it's actually a fairly large signal, but very subtle because you have to dig it out of the polarization maps of the cosmic microwave background. And we have to look for specific patterns, which are volts kind of things. So you can see this pattern of polarization has handedness. And these are telltale signatures of primordial gravitational waves that we are looking at. But these are still, undetected, and we are seeking that out, right? So what we are trying to do is, these are the things measured in the cosmic microwave background already, the ones in red and blue. The green is only measured here, but we haven't measured this part, which actually has this signal of gravitational waves. And we want to now, this is what the current capability of the last space satellite was, Planck. And we want to send out another space satellite, which has much more improved sensitivity. So we want to do our near ultimate polarization survey, and which will reveal the signatures of quantum gravity, because the primordial gravitational waves arise from inflation, are believed to arise from inflation, and through a quantum field theory and curved space-time process. And detection of those will be a big vindication of our approach towards quantum gravity. Okay, and besides, it will have many other things, many other very, very exciting science of neutrinos and dark matter that it will bring out. So we made a proposal in 2018 to ISRO to be, take a major role in an international CMB satellite, 4th generation satellite. This was done by an Indian cosmology community, and this involves a 2-ton satellite, which is fairly large, 4 meters height, 4.4 meters diameter, but it fits into the largest launch vehicle we have, the GSLV Mark III. And we have had quite a few discussions on this now. And this will be launched to the second Lagrange point, and which will sit there and map the microwave background at unprecedented accuracy, sensitivity. To do that, why again are we interested in this? Because the detectors that are used in this are absolutely amazing. Each detector is capable of, detecting attowatts of power. Okay, these are far more sensitive than what you have in, commercially the 5G technology. In fact, 5G technology was in the lab in late 90s. And what we are talking about is 2 decades from then. We have these detectors already in the labs. And you can make big arrays of this. So you can put 2,000 or 8,000 such detectors onto the focal plane of a satellite and send it off. So that's the exciting thing that I look forward to in the decade ahead. We have, a third generation satellite which has done a lot of great work in cosmology, but we still have more to learn, and particularly detect, open up the new window in gravitational waves on the cosmological scales with CMB Bharat. And no, so that's a hope for the future. I'll stop here, and thank you.
Okay, thank you, Professor Sorodip. Thanks a lot for the wonderful talk. And I think that the session is now. Any questions, please, from the students, postdocs, faculty members?
Tapoda, may I ask a question?
Of course, Sanjeev, please go ahead. Please.
Okay. Torunda Sanjeev here.
Hi.
Hi. So Torunda, in 2002, we started the era of neutrino astronomy through the Nobel Prize to Koshiba-san and Ray Davis Jr. So could you please suggest that, now we are living in the era of gravitational wave astronomy as well as improvements in neutrino astronomy. So how you see that these two, era or these two landscapes can be, merged together to get the unified picture of the standard model, which can explain everything?
I don't have what you would say. I mean, are you talking about the Indian situation or the global?
No, I'm seeing in the global perspective point of view.
Global perspective, I'm not sure if the gravitational wave observations will have any strong bearing on neutrinos, other than the fact that if there are events, gravitational wave events, which are accompanied by neutrino emission, those are looked for. For every gravitational wave event, we also the neutrino observatories. So there are joint papers which put limits on neutrinos. We haven't observed neutrino emission from any of the events that we have currently seen. Okay, so that is in terms of that. In terms of cosmology, the primordial gravitational waves, as a quest to get the primordial gravitational waves, the satellite that we are talking about will also help measure the neutrino masses to a level where it will be, we can only measure the total mass of the neutrinos in cosmology, but we will measure it to a level where it will be comparable to the larger mass gap, mass difference that we know of. And so it will kind of help sort out the hierarchy in neutrinos masses. To that extent, I'm aware of. If you are talking about big efforts, of course, having INO and things like, and LIGO India, these are projects in India, and it's important to have these. I mean, so when I was talking about LIGO India first time to Dr. Kakotkar, he was one of the first people I talked to. He said that, for a country of like India, there should be 4 or 5 such projects happening, because these bring in frontier science and frontier technology together under some umbrella. And I think INO, the neutrino community, and now the gravitational wave community have done that. I mean, we see that happening, and that's very important. And I personally, again, there can be differences in I think having the facility in India makes a huge difference.
Right.
participation in us. So in that sense, there's a lot of synergy. I mean, with INO, I mean, in fact, we were informed a lot by what INO went through, because they were, the elder sister in the thing. So they faced a lot of the technical challenges which we managed, or standard challenges of big projects that we could evade.
I think since you have raised this, like the in situ development of technology in India, that industry takes part in basic science, I think all these projects will make that bridge to happen basically.
Yeah, it will force that to happen.
Yeah, because I think if we sit down and look forward, there are lots of technologies which can be used in both the experiments at the basic level, and you engage the young minds over there. So I think, at the ground level, there are a lot of synergy. But my question was prompted by the discovery of this source of high energy astrophysical neutrinos. If you remember, 2.5 years back, IceCube claimed at some confidence level that they could, understand what is the possible source of one of their event. And, that confidence level increased when they also saw the signal in the gravitational wave detectors, basically, because there was a joint paper by IceCube and the gravitational wave people. So I was just thinking that, whether those things are also under consideration.
No, those are definitely. So that is, these are, so it's a vast collaboration, and there are, working groups which are working on this very strongly. So no, definitely gravitational waves. First of all, one should realize that every time you have opened a new window,
Right.
there have been surprises.
Right.
Till now, the surprises have been very mild. Of course, the masses of the black holes we have detected was a big surprise.
Right.
But it was not a phenomenal surprise, right? We know black holes exist, neutron stars, but it will be very, very unusual if this community does not, come up with something which is extraordinary, right? Which was absolutely not anticipated, and that would be quite a surprise. In fact, every other window we have had big surprises, pulsars, quasars,
Right.
and of course particle physics. There's a lot of things.
Yeah, I think we need to just keep our eyes open and make the synergy.
Yeah, but my main point is, since we are discussing this is not a question answer. I think we need a baseline. We keep talking about getting great science out of India, but you have to create a strong base from which people can get launched. We don't have that at all.
Yes.
And to create that, I'm not saying the mega sciences will create it. These are small efforts which try to actually tell you where the baseline is. And I think we are missing that fact continuously.
Yes, Torunda. Yes, I completely agree. Yes. Thanks.
Okay. So, Sanjeev, any other questions, please? Okay. If not,
can I ask a question to Professor Amit Rai?
Yes.
How do you feel about the story now?
Oh yeah, it's great. I mean, I'm really thrilled that this has really come off, and you are making progress. Because something I remember in 2010 or 11, I think we were Rono and somebody else.
Rana and
and the deputy director of LIGO USA. They came to our lab, and they were going around India and talked about it. So of course I told them that this is you have come to the wrong inter-university center. You should go to IUCA first. But anyway, that so it was really something. I mean, I've been looking forward to it, although I was not directly involved in any time. But I think we had lots of discussions with Dr. Kagodkar and Professor Kaur also.
Right. No, those initial years actually, which I keep referring to. That's why I want to point out that the encouragement we got from senior people, kept this project alive, and we hope to deliver.
No, thank you, Sir Tarudi, for your presentation. It's a very nice presentation. You summarized it beautifully, and also brought out the physics as well as the technical challenges. And connected with Sanjeev's thing, and in fact, you will see in my presentation also about the particle physics and the accelerators, where we are also looking at the same thing, that building the baseline of technology in the country. So that, and I agree with Tarun when he says that you have to unless you have the baseline high enough in international standards, you cannot have breakthroughs. Because I believe its breakthroughs are always some fluctuations, which is usually 3 sigma limit, as we know in particle physics. You have to go to 5 sigma. So unless your baseline is high enough, you cannot really go into that
or make
regime.
an impact rather.
Yeah.
Okay, thanks, Amita, for your encouraging comments. And Tarun, we all would look forward to the grand success of the project. Thank you very much, Tarun, for your kind time and joined all of us. And with this, I would like to conclude this particular talk and hand it over to Professor Suresh Patra. Thank you very much.
Thank you, Topapa. So I just wanted to mention I have some other engagements, so I will not be able to stay on. I hope that's fine.
No problem, Tarun. I understand.
Okay.
I mean, no problem. Please go ahead. It was a huge.
Thank you. I'm sorry, Professor Rai. I will have to go because there's.
That's okay. That's okay,
Yeah.
Tarun. Yeah, go ahead. Yeah.
Yeah. Please.
Okay, should we start the second talk or will we wait another 1 minute or 2 minutes, I think?
Yeah. We can get started, I suppose, Suresh?
I think so, yeah. So first of all, on behalf of IOP, we welcome Professor Roy to this second talk. And we will talk about accelerator and structure of matter. And before going to the lecture, let me introduce him. And it is really a great pleasure. And I feel thrilled to introduce him. Actually, whether I am capable to explain him or not, that's a different thing. But anyhow, it is a great pleasure for all of us to find Dr. Rai here in the foundation talk. And he did his master from Delhi University and PhD from IIFR Mumbai. And he joined there till 1990. And after that, he went to Florida State University as a postdoc. Then he was a visiting scientist in many of the international labs like KVI Netherlands and Argonne National Lab USA. And in 1991, he joined IUAC, Inter-University Accelerator Center. Earlier it was known as NSC, Nuclear Science Center, in 1991. Then he became the director of IUAC from 2001 to 2013. And he did so many pioneering work there. And after his retirement, he came to VCC as a Rajaramana Fellow. And now he is a guest lecturer in Indian Association for Cultivation of Science, Calcutta, and an adjunct professor in Manipal Center for Natural Science. And he is a fellow of the National Academy of Science, India, and eminent scientist. He got Eminent Scientist Award by Indian Nuclear Science Nuclear Society. President of Indian Cryogenic Council for 2 terms. Chairman of Asian Committee for Future Accelerator, 1 term. And he has written a book, Great Experiments in Physics. And if you talk about accelerator, that means Amit Rai is the accelerator. So you cannot tell anything about accelerator without him. And he has contributed many labs. I think before 30 or 40 years, there was no accelerator in India. Almost there was not. Even he has visited many times to IOP. So he is more or less very close to IOP. And he, at the time of the formation of our IBL, he had come many times. When I was a student, I saw him here. I have interacted with him. So he is really an inspiration for all of us. And there is no end if I talk about him. So I invite him to this talk. Professor Roy.
Thank you, Suresh, for your kind introduction. And also, I thank the organizers of the 47th Foundation Day of the Institute of Physics for giving me this opportunity to speak to you. And as Suresh said, I have visited IOP for a number of years now, almost 4 decades of connection with this institute. And I think I remember last I gave a talk on the Foundation Day of I think 2015 at IOP. At that time, that was in person. Of course, this would have been also much better if it was in person. But nevertheless, in these times you cannot travel, so we have to be satisfied with what we have, online presentations. So this is as Shuri said, and Tapo also, I must thank Tapo for contacting me on this, and he gave me the suggestion that I should talk about accelerators. So because that has been my passion for the last almost 3 decades. So okay, well, let's start with that. I think most of many of you, let me just first of all start the presentation. Entire screen, and then no, I shouldn't take the entire screen, I guess. Yes, entire screen. Screen 2. Share. Oh, sorry, I think I got the wrong screen. Let me just try to get the right. Stop presenting and get back. Are you able to see my screen?
Yes, yes. Yes, it's clear.
Okay. Why is it not changing? Not able to change the slides for some reason.
So could you please come out of the full screen mode?
Yeah, I think let me do that. Exits full screen. But still, I can't seem to be changing the. Let me just give me a second. I'll do that. I'll do it again.
I think you may open the file again, closing it.
Yeah, I'll do that. Let me get back. I think I have to, sorry, I log out and come back. Why am I not able to share the thing? It just says cancel and not allow me to share.
Sir, did you log out?
No, I didn't. I didn't. Present entire screen. Still, it's not allowing me to share now this time. I will come back again by logging in. Okay. Oh, okay. All right. Now I think I got it. Should be coming now.
Yes.
Yeah, there. Are you able to see my screen now?
Yes, yes.
Okay, good. Good. Sorry, I got this. I was trying to put it in a bigger screen, but that got into problem. This slides. Anyway, so let's start with this accelerator and structure matter. Many of you in this audience
Sir,
today.
Below in your slide, there is a icon is there. You hide that one, then your full screen will be visible. Right? Yes.
Hide the screen. Yeah. Okay. All right. I've done that. And yeah. So we today, if you all those people, all the participants in this talk, in this celebration, Foundation Day, those who are in the audience, many of you, if not majority of you, have had an particle accelerator sitting in your home, and you have sat in front of it for several hours at times. It is the humble television set before the advent of the plasma and the LED technologies, the ones which are the old tube types, and that housed an accelerator. It's a cathode ray tube, and it is with that the first fundamental particle also was discovered. So coming to particle accelerator, how do you define a particle accelerator? I start with that basic definition. A particle accelerator is a device in which a charged particle gets accelerated in passing through an electric field. Now, what is required in an accelerator to build an accelerator? There are various components, and I'll just listed them for, I mean, most of you already are familiar with it, but just as a completion, for completeness sake, I'm listing the various components which come in. First, we need a source of electrons or ions. And this could be of different types. It could be a discharge type of source, like a penning gauge, which you use in vacuum measurements. It could be a plasma device, like a electron cyclotron resonance source, or it could be a sputtering source. And in fact, in the 3MV Pelletron at IOP Institute of Physics, you have this sputtering type of source, which is used for the ions. And then it is the source of electrons and ions, whichever you want to accelerate. If you want to accelerate electrons, you have to have an electron source or an ion source, heavy positive ion source. Then you have an accelerating structure which accelerates the particles, and this consists of two or three things. The one is there will be a series of cylinders, metal cylinders, separated by some gaps in vacuum, all stringed and coaxially linked, and across these cylinders you put high voltage of opposite polarity in such a way that the polarity will change as the particle goes through the gaps. That means the voltage that you put, if it's a DC voltage, then it is a gradient of voltages put in across the electrodes. If it's a electrostatic, but if it's a electromagnetic accelerator, if you use the RF accelerator, then the voltage will alternate, and the particle has to be in phase right at the gap with the accelerating field, so that the electric field points in the direction of the axis and it gets accelerated. The other way of generating very high voltages is a cavity resonator, and I'll come to that later on. The cavity resonators can build up very high fields, and then this you can line up, connect it to the electrodes, these cavity resonators, or the cavities could itself form the electrodes, part of the accelerating structure, and the particle goes through these cavities and gets accelerated when the field is lined along with the particles in phase. Then there is the other part is the beam guidance and transport. So from the ion source to your target place where you want to study your the whatever reactions or the induce any change in the material that you want to study, there you take these accelerated particles, so they have to be guided and transported through that. So what do we do with the devices that we have for doing that are the bending magnets, magnetic or electrostatic lenses to focusing the beam, beam steerers which can move the beam, position in the beam at any point which you want within your target, and then you have the Faraday cups for measurement of the beam currents, and beam profile monitors which tells you where the beam is inside in the accelerator, precisely the position, XY position, and the size. Then the entire thing has to be enclosed in high vacuum, and very high vacuums today the vacuums of the order of 10⁻⁻10 to 10⁻even 12 millimeters of mercury have to be achieved at the very high energy for heavy ion accelerators that we have today. And this is done with very different types of high vacuum pumps. And I think in the Institute of Physics you have quite samples of each of these items which I mentioned. And finally the power supply which generates the high voltage. It could be either DC or RF, and you have these high voltage generators and RF power supplies. Now the first, as I told you, that the TV set houses a cathode ray tube, in which the electrons are generated and then transported accelerated by certain potentials, and then hits the target. The very first tube of cathode ray tube, which was used by J.J. Thomson in 1895 to discover the electron, and the electron was the first elementary particle to be discovered by human beings. And many of you have already, I don't know whether these days in the BSc labs or MSc labs this experiment is there. At least in my times, the E by M of electron was measured by using a cathode ray tube like this, very similar to the one which Thomson used. And the length of this tube is about 30 centimeters. So this is the first accelerator made by human beings for accelerating electrons to few kilo electron volts. The next stop in this journey for structure of matter and accelerators, how it came. Actually, this Ernest Rutherford was the instigator and for building accelerators in the whole world. He discovered, as you all know, that he discovered the nucleus in 1911 through his famous alpha scattering experiment on gold, which we read in the textbooks. It was the experiment actually was done by his colleague Hans Geiger, as assistant, and his student Marsden. In fact, they did this experiment, and it was not really as an aside. The experiment was not just single experiment of alpha particle scattering on gold. It was actually a series of experiments done from 1908 to 1910 for 3 years. Geiger and Marsden did an extensive experiment of scattering of different types of the alpha particles from the radioactive source on different materials, and studied the Z dependence, the thickness dependence, etc., and the angular dependence. And finally, which is shown in the textbooks today, is the alpha scattering from gold surface, from which Rutherford got the idea that there must be the positive charge, almost the entire mass of the atom is concentrated in a very small, tiny volume, which is called which is termed the nucleus. And then after that, being the researcher, the great scientist he was, he immediately wanted to study the nucleus. What is inside the nucleus? He wanted to penetrate that, and so he said in 27 in a physical society meeting that what we require is an apparatus to give us a potential of the order of 10 million volts. I see no reason why such a requirement cannot be made practical. So he wanted these high energy particles, because only particles available to them as a beam was the alpha particles from radioactive sources. The number was very small and the energy was also fixed. So he wanted a variable energy source as well as a high intense beam. And what you can do with these high energy particles? You can do 3 things, as I put it. We can take snapshots of the system. You can take image of the system. See, normally when we see any photograph or something, or you take photographs or try to resolve the constituents of a system, you can resolve two particles if they are only separated by more than the wavelength of the light that we use to see the objects. Now, with light, that's why with the visible light, you can separate particles which are separated by about a micron separation, because that half a micron is approximately the wavelength of yellow light, or mean wavelength. Now, if for smaller separations, for finer resolution, you have to go to the higher energy and lower wavelength electromagnetic rays, like the X-rays or the gamma rays. Now, that you cannot vary. There is a limitation to that, and the intensity especially for very low, the smaller wavelengths, high frequencies, that means in gamma rays, the sources are also very scarce. You cannot have too many. You don't have too many sources, natural sources yet. So the alternative is to take the help of the de Broglie wavelength of a particle. Now, the de Broglie, we know that it is inversely proportional to the momentum. That means square root of the energy. So if you increase the energy of a particle, then the associated wavelength goes down, and that can probe and resolve particles inside. If you want to see inside the nucleus, you have to have the wavelength which is of the order of smaller size than the nuclear size, which is of the order of a Fermi, which is 10⁻15 meters. And that you can do with high energy particles. Now you can excite, if you need to find out something inside a closed system, with a bound system, you have to excite it by an energy comparable to the binding energy system. Then you can see what is inside. You can really shake it up and see what kind of how it talks to you. So you can also, the second thing is that you can create new particles if the energy is double, greater than twice the mass energy of the particle. And also the accelerators can take us to very high energy particles when they collide. Then for a very, very tiny volume, your energy density, it goes up extremely high, and you can go back in time, as in the previous lecture Professor Sauradeep was talking about the events that was going inside the black holes, mergers and so on, or in the even earlier than that, at the time of the Big Bang, very close to the Big Bang. So we can have mini banks, you can create mini banks in the laboratory by shooting very high energy particles on each other. So you can go back in time and see what physics was going on at that kind of event, at that time of at that high energy densities which I was talking about. Now we come to the different types of accelerators that was built for that. And in my talk today, where in the next rest of the talk, I will talk about how each type challenge came to the accelerator community to build energy, to increase the energy from the point of view of physics, and from the point of view of what to study at still higher energies. The accelerator community also rose to the challenge and provided an answer to that. And this development of the nuclear and particle physics went on went in parallel with the development of the accelerator energy, particle energies. So the very first, in the 1920s, after the Rutherford's call, there were a lot of activity in Europe, in different laboratories in Europe, and right there in Cavendish laboratory where Rutherford was, his students John Cockcroft and Ernst Walton, they started working on accelerator. It's a very small, it's a very simple device, actually using a voltage doubler circuit, which anyone who studied electronics is a very common circuit for voltage doubler circuit in electronics, where you use a capacitance and a rectifier combination to double the voltage. And so you can stack them up and you can create higher voltage. The only limitation comes from since the insulators cannot hold more than a megavolt or so. So 1 million volt is almost the limit for such an accelerator. This is called the Cockcroft-Walton generator, or the cascade generator. And with the very first one which they built, which is shown here in this photograph, they reached an energy of 400 kilovolts. And with that, they bombarded lithium-7 and produced the very first nuclear reaction produced by human beings on this planet. And that is this lithium-7 400 keV hitting lithium-7, creating 2 alpha particles. And for all their trouble, they were awarded the Nobel Prize in 1951. Around the same time, 1931, further development of the electrostatic accelerator went on by Robert J. Van de Graaff in the US. He created the Van de Graaff machine, and in fact, the Institute of Physics Pelletron is a version of the Van de Graaff, where in the Van de Graaff's case, Robert Van de Graaff used a insulated belt for transferring charge from the ground to the terminal potential, whereas in the Pelletron, this belt is replaced by a steel, like a cycle chain, steel pellets linked by insulators, a chain. And the Pelletron has a slightly more, some advantages over the belt drive. That is because it has more stability. This was in the electrostatic development. And in the parallel side, in Europe, there is a Norwegian Rolf Widerøe, who actually following the work of Gustav Ising, he thought that he should use the RF volt frequency, alternate current, and he had this idea of the linear accelerator, where he put this metal electrodes, tubes, cylinders in coaxially, and applied alternating voltage to them, and such that as the particle comes to this gap, it gets accelerated. And then at that time, suppose this is negative and this is positive, By the time the particle travels through this tube, which is a field-free region, and comes to the next gap, it gets accelerated again. Because the phase has changed by pi, and so it gets kicked further. Now, when he proposed this idea, his mentor, his supervisor, told Widerøe that this is a crazy idea; it will not work. So you you give up and take up some other problem for your thesis. But Widerøe was a very stubborn fellow, and he continued with his idea, and he succeeded. So for the students who are in the audience, so you should not always believe your supervisor. If you are convinced about something, go ahead and do it. So Widerøe succeeded in that, and he got a 50 kilovolt. He could get potassium ions with 25 kilovolt drives. And these equations, he put it up. He wrote a paper in Archive for Electrotechnique. And now in this, what happened was that around the same time, 1929, there's a young professor, Ernest Lawrence, who was just appointed professor at Berkeley at the age of about 28 or so. And he happened to read this paper in German. But unfortunately, Lawrence didn't understand what is written because it wasn't written in German. But he could see the diagrams and follow the equations. And he understood that this is the principle of the linear accelerator, with the RF. The phase has to be matched. But then he had a brilliant idea that he said, well, I'll put it in the magnetic field and then let the particle go around in circles, and I can, with the same electrode combination, gap electrode, 2 electrodes, if I put it in the form of a D, then the particle can keep circling around with the same, in the same enclosure. I don't need any more metal pieces here, and I can get some energy by this. So this was the invention of the cyclotron, and nature was kind to Lawrence that the frequency of this revolution is the cyclotron frequency, which is independent of the particle energy. So he just had to have one magnet and a chamber, and this particle could always be in phase across this gap. If once it's set, the frequency is set. So with that, he and his student Livingston, they made this first cyclotron, which is shown here. It's only 4.5 inch in diameter. You could hold it in your palm of your hand, and it accelerated protons to 80 kilovolts. But then this was in 1931. And then, of course, after that, Lawrence built several cyclotrons. He kept on building bigger and bigger machines. And final thing which he built was in 1939, about 184-inch synchrocyclotron, which was 350 MeV. It was in the 40s, in the early 40s, he built this cyclotron. So this was the biggest cyclotron built by him. Now, with this, so this is the parallel, and then there was a big burst in the machines, in such building such machines. Only after the World War II, during the World War, the RF technology got very much improved because of the radar, because the demands of the radar technology, radar systems, used in the wars. And so at that time, technologies are available for high power RF amplifiers, and these were used to build higher and higher energy particle accelerators, which I'll show you a little later. Now, in the 50s and between 50s and 70s, 1970, large number of accelerators are built. So I have classified them and I have not go through each of the accelerators, but then they can be classified in 3 categories. One is low energy accelerators, which I call energy or particles less than 1 million electron volts. And with this, what can you do? You can do lots of material studies, material modifications that can be done. You can use a study for doing atomic physics, like you can do plasma ion processing, you can do focused ion beams, you have ion implantations, you have in the Institute of Physics, all these 3 things taking place. Then you can do atomic and molecular physics. You can dissociate molecules by highly charged ions. You can do inertial ionization processes with multiple charges. With the ECR, electron cyclotron resonance source, you can make highly charged ion, and with that you can study that. At IUSC, we have a couple of these systems in place in Delhi. You can do neutron generation. you can do accelerator mass spectrometry with carbon-14, which you also have at IOP. Then you can do secondary ion spectrometry, and you can also, very importantly, measure low energy cross sections for nucleosynthesis. That is how nuclei are formed, synthesized in the stars, or even in this neutron star mergers and so on. The next category of accelerator, which I call medium energy ion accelerators, are in the range of 1 to 10 MeV per nuclear mass unit. So with the heavier ions, it will keep on, the energy actually will be higher. So with this, these are used mainly for nuclear reaction and nuclear structure studies, because this is the range of 1 to 10 MeV per nucleon. You remember the binding energy of a nucleon, that is proton or neutron, is of the order of 7 to 8 MeV. And so if you can have 1 to 10 MeV per nucleon given to the nucleus, you can study the dynamics of the nuclear reactions without breaking it down, without breaking the nucleus completely. So you can study the nuclear structure and dynamics of these reactions. And also this can be used for these production of elements in stars and supernova. This is slightly higher, because when you come to heavy ion fusion reactions which are going on in the stars, you need slightly higher energy than of the order of, again, the few MeV per nucleon. You can produce the super heavy elements, and you can do mass spectrometry with the heavy elements. Also can be in material modification. It can be studied. It can be used for swift heavy, for the material engineering and characterization, because now with these energies, the heavy ions can penetrate slightly on deeper level into the material. So you can do embedding of different materials at different layers in the matrix that you have, like in a semiconductor. So in the semiconductor industry, you have all the semiconductor industries, they use small, low energy and medium energy ion accelerators for modifying the materials. These can be used for cancer therapy. The low energy ions can be used for cancer therapy on the skin cancers and so on. You can study the radiation effect in biological systems and also atomic structures. Now we come to the last category, that is high energy accelerators, energy greater than 1 GeV, that is 1000 MeV. These are used mainly for fundamental research connected with high energy system, that is structure of nuclear particles. You can go into quantum chromodynamics, studies of those, the relationships of chromodynamics, and see whether how far it extends. The symmetry laws, you can study the symmetry laws, breakdown of symmetries that have been studied. You can study the quark-gluon plasma state of matter. And this high energy accelerator has an application also, which time permitting, I will tell you about accelerator driven subcritical systems in energy production and waste disposal. Okay, so now let us look at a very quick look at what we have learned about the nucleus and the particles scenario, high energy physics, through these accelerators that have been built over the years. We have learned about the nucleus, that nucleus is unlike any ordinary matter. It's made out of protons and neutrons. We have already read in the textbooks. Size is at the order of A to the power 1/3. A is the number of nucleons. A to the power 1/3 Fermi is the size of the nucleus approximately. It has extremely high density. It's 10 to the power 14 grams per centimeter cubed. It has very high binding energy, which is of the order of 80 MeV per nucleon. About the nuclear force, we know that it is moderate. At moderate distances, it is of the order of a couple of 1.4 Fermi and above, 2 Fermis, it is attractive. But when you go to shorter range, less than 0.7 Fermi, it becomes repulsive. This is what we know. We know the approximately the forces we know. We do not know the exact shape of the force, because we cannot calculate it ab initio. It has to be, because we know that now we know that the neutrons and protons have the quark structure. So the nucleon force, the interaction that we know of, is not really the fundamental interaction. You have to build it from the quarks, and that is a work in progress yet. About the nuclear structure, we reasonably understand the nuclear structure of nuclei at low excitation energies of a couple of MeV, 2 to 3, 4 or 5 MeV. Up to that, the excitation, the spectra the excitation levels, the quantum states that the nucleus goes through, that we understand by building models. Because we, again, as I said, with nuclear interaction is we only model dependent nuclear interactions, because we don't know the fundamental, we have not been able to calculate the shape of the nuclear interaction ab initio from scratch with the elementary particles, which are in our case is the quarks and gluons. They will be giving us the final form of the things, and that's, people are still working on this at this time. So the next thing is, we have been able to produce lots of elements in the laboratory. Beyond, we have able to extend the periodic table from the 92 elements that are known naturally. We are now to date, we have the heaviest element produced is the proton number 118. That is called, given the name of Oganesson, following the team led by Oganessian in Dubna. In his honor, it has been given. And I've listed in the last couple of decades what the ones which have been found. Meitner was found a little earlier, about 3 decades ago. So these are the heavy elements which are been produced in the laboratory. They are almost, of course, not stable in that sense, that you can find them on the Earth or anywhere in the the universe at the state, because they are metastable. Some of them live for very short time, like milliseconds, or even some of them even microseconds. But for the nuclear physicist, if the time is metastable nucleus, we can study if the lifetime or half-life is much longer than we call them the metastable state. If the lifetime is stronger than the strong electromagnetic, the time scale of the strong interaction, that means the amount of time that a particle takes to cross the nucleus. So those are called metastable states, and we are able to study them in the laboratory through various techniques. Now, in the particle physics, I'll just go through the various the accelerators were built at higher and higher energies, and each of them gave rise to a new discovery in the particles. It started with from the 50s. The cosmotron in BNL was built at 3.3 GeV. It's a ring structure of it's a supersynchrotron type of machine, and then this was used for study the decay in K meson, K naught neutral K meson, and there's the anomaly that the parity violation was discovered in that by these two Chinese Americans, Yang and Li, and the experiment was done by following that parity violation. It was confirmed in the actual radioactive decay of cobalt-60 by Madame Wu in Colombia. They were all in Colombia at that time, and the Yang and Li got the Nobel Prize in 1957. And some people are not very happy that the Madame Wu was not given this prize, because she also seemed to she deserved that prize as well for actually verifying in the laboratory that the parity violation is observed in beta decay in weak interactions. And the next machine was in Webertron Berkeley at or at the same time in the 50s. That went to 6.2 GeV. There was this kind of the rivalry between BNL and Berkeley at that time. So they went to 6.2 GeV. With that, Segre and Chamberlain discovered the antiproton in 1954, and they got the Nobel in 1959. The other center for linear accelerators was developing at Stanford, because the Stanford the klystron was discovered by 4 people, and that klystron boosted the power of the RF to such a large extent that they could use it for the linear accelerators of a reasonable length they could produce, and they produced about 350 MeV protons with that. this is an electron machine. Mark II was electron machine up to 1.2 GeV and Stanford. With that, Rolf Hofstadter, he measured the distribution of charge distribution in the inside the nucleus, and from that he could find the relationship between the nuclear radii and the mass number, and that radius of the nucleus goes as a to the power 1/3. Nuclear number to the power 1/3 was found out by Rolf Hofstadter in his experiments. The next discovery with the machines, the next machine was the alternate gradient. The machine at Brookhaven National Laboratory was upgraded to the alternate gradient synchrotron, and with that, the team led by Lederman, Schwartz, and Steinberger, they discovered the muon neutrino, establishing the second type of neutrino. And they got the Nobel Prize as well. And with the same machine at BNL, the CP violation was also discovered in the K-meson decay, and this Cronin and Fitch was awarded for the Nobel Prize for that. The next leap of the linear accelerator came from Stanford, where they had built the 2-mile long Stanford linear accelerator for up to 20 GeV for electrons in '66. And the person responsible for this at that time, the project was Wolfgang Panofsky. I don't know whether you read the Panofsky's. We read the electrodynamics book by Panofsky in college days. Now I don't know whether there's any more used or not. But Panofsky was a great accelerator builder and physicist, and he did that. And with this machines at Stanford, of course, now it has served its purpose as a particle physics machine, and it has been converted into a photon source. With this machine, these three gentlemen, Friedman, Kendall, and Rich Taylor, they did the same experiment, repeated the Rutherford experiment or even Hofstadter experiment, scattering from nuclei, the high energy electrons. And now with 8 GeV electrons, they could probe smaller distances, smaller length scales, and they found the deviation, they found the substructure in the proton. Now, in this scattering plot, the cross section versus the q square, the momentum transfer square, and you find that if the proton was going to be a point, had no structure at all, a single entity, then the curve should have, the scattering cross section should have dropped like this, by given the dashed lines, whereas the actual experiment points are much flatter and went like this. And you can see that with energy also it changes. It becomes flatter as you go to high. Sorry. As you go to higher energies, it becomes flatter still. It becomes flatter at higher energies. So that means that you probe smaller particles, that there are small particles embedded inside the proton. That means the protons have substructure, and the size was less than 10⁻15 meters, obviously. So with this was the actual experimental evidence for the substructure of protons, which are being postulated at that time, around that time, and Gell-Mann had already postulated the quarks, and Feynman had also postulated the parton theory. So this was taken as the confirmation that the proton has substructure, and quark model got a big boost from this experiment. And these gentlemen were also awarded the Nobel Prize. Now, this is so far I have described the fixed target machines, where you have a particle beam coming at a high energy and hits a target, and you study the reactions. Now, there is a problem with this when you go to relativity. Relativity brings in a problem, because you cannot you want to get energy in the center of mass system. As you very well know from momentum conservation, momentum energy conservation, that if a particle comes and hits a fixed target, a target which is in the lab frame zero at rest, then the part of the energy of the incoming projectile will get transferred into the center of mass motion, and a part of it will go into the excitation energy. Now, the excitation energy is given only by excitation energy that is available is given by the mass of the target, proportional to the mass of the target, and the energy projectile to the power half, square root. So if you increase the energy, the available energy in the center of mass does not increase that much. It increases only to the power half square root. So it increases much slower. But if you have a particle and both the particle and the target are moving opposite to each other, then it is called a colliding beam machine. And you have MP and MT travel in opposite direction. The center of mass energy is actually proportional to the energy itself. So E square is proportional to EP into ET. If they are the same energy, let's say, then you have the E would be about twice the EP, the projectile. So you get all the energy that is available for you in the center of mass for the studying, exciting the system. And this was for doing this colliding beam. Now, if one beam is all right, you can bring in now the other beam to bring in and to be on a spot, because the particles are of course very tiny, and the spot size to the number, the encounter probability, it depends on the number each, the flux per, the number per centimeter square in each beam. So if you have enough particles, then only there is a high probability of collision, because the particles themselves are extremely tiny. So to increase the flux, you have to squeeze them more and more so that they are in a tight bunch. The tighter the bunch, the better the flux would be, what is called, we call it luminosity of the reaction. To increase the luminosity, you have to reduce. That means what you have to do, tighter bunching is possible if you reduce the transverse momentum of the particles and keep the longitudinal momentum intact. So transverse momentum of particles can be reduced, and that is called the cooling of beams. So there are two ways of was suggested. One by Gersh Butker from Novosibirsk. He suggested the electron cooling, that you have a proton beam, for example, going, and in parallel you put an electron beam of the same velocity. Then the electron proton collisions at that high energy, the recombination will be very small at that high energy, but the electrons will take away most of the transverse momentum. So the protons will get cooled. That means they will get bunched much better. They can be. The other method was given by Simon van der Meer. He at CERN. He was working at CERN, and he said stochastic cooling. That means in a ring, if a particle moves in a ring, and you have the particle going in, and you measure the transverse momentum at one point by your beam profile monitors, etc., and then you transmit the signal to the opposite side of the beam much faster, because the particle will be slower, even if it's relativistic, it will be still slower than that of light. So you can transmit the signal faster and then make the correction in the opposite side of the ring. The momentum, the transverse momentum, gets cancelled out. So this you do random number of times with the bunch beam. The stochastic in a statistical way, the particles, they will lose their transverse momentum. You can reduce the transverse momentum. This he showed. He proved that he worked out the theory, and he demonstrated that in practice. And this was employed at CERN, and we'll come to that later, the effect of that. So these colliders were then implemented at Stanford and at Brookhaven, the collider for electron-positron colliders. And with these machines at two places, the first discovery came in 1974, that of the Jepsi particle, which is called the charm quark, by one group led by Barton Richter and the other led by Samuel Ting. Richter was the leader of the Stanford group, and Ting was the leader of the Brookhaven group. And this was also awarded the Nobel Prize very quickly in 2 years' time. And see, 74 it discovered, 76 they were given. Now this was charm quark, and these two gentlemen, Japanese gentlemen, Makoto Kobayashi and Toshihide Masukawa, they had worked on this. They working on the quark theory. They found out that if we consider the CP violation, to explain CP violation, they had to include another set of quarks. The quarks was at that time the known quarks were up, down, and strange from the various decays, and then this charm was found. Then they theorized that there should be one more set of quarks, which is the B and T, bottom and top. Another generation was necessary to explain the CP violation observed in the K-meson decay previously by the Val Fitch and Val Fitch and What was that? Yeah, the CPU 64. The CPU violation was discovered before. So the bottom quark afterwards, the C quark was found by the charm quark was already found in 74, and the bottom quark was found in about 3 years' time at Fermilab by Lederman et al. In one experiment. And the corresponding third lepton for the, they also said that there should be, since there are 3 neutrons, now people expected that there should be 3 sets of quarks also, and the 3 sets of quarks are there, and 3 sets of leptons must also should be there for symmetry consideration. For not, there is no fundamental theoretical reason that they exactly have to match, as far as I know. But then it's from making it symmetric system, that 3 generations of each particles. So the tau lepton was also predicted, and that was discovered by Martin Pearl in 1975 with using the same SLAC machine. So the other experiment, the colliders also kept being built elsewhere. The electron-positron collider was built in Germany. One was at DAISY. There they discovered the gluon, which is in a 3-jet event in 1979. And at CERN, super proton synchrotron was built by the leadership of John Adams. This was 270 GeV proton, which was converted later on to PP bar collider by this by the principle which was discovered by Simon van der Meer, the cooling of stochastic cooling. And with this machine, Carlo Rubbia at that time was Director General, and he had this idea that he was the instrumental in giving support to van der Meer to make the that antiproton, the cooling of antiproton beams, which is necessary for injecting into this superproton synchrotron and made it into collider, PP bar collider. And there to discover the W and Z boson particles, communicators of the weak interaction, which are postulated earlier by these gentlemen, Sheldon Glasser, Abdus Salam, and Steven Weinberg earlier. So all of these discovery theory, as well as the, in this case, experiment, both were rewarded with Nobel Prizes. The next step in the accelerators in the higher energies were the large electron-positron collider at CERN, which was went to 100 GeV, and which was considered to be kind of some kind of a limit for the synchrotron for the radii. And this was at that time the largest tunnel was built at CERN, which is 26.7 kilometers long, and this has been replaced by the LHC. From that machine, the idea that only 3 light weakly interacting neutrinos are there were established, generating which has provide some kind of a convoluted way of support for the 3 generation of quarks and leptons. And this was by the study of the decay of the Z boson, the neutral Z boson, for the decay width. From that, it can be inferred that there are only 3 light weakly interacting neutrinos. But again, there is no very great big theoretical basis for that. This is experimentally observed from all the experiments match with this concept that there are 3 generations of quarks and leptons. Around the same similar time at the 80s, the Robert Wilson had built the Fermilab laboratory, and in that during Lederman's time, they changed the Fermilab's rings to go up to 1 TeV proton-proton collider, because they want to be a little they want to reach the TeV barrier, and they succeeded by introducing a new technology, which is using of superconducting magnets. So larger magnets were used so that in the smaller ring could accelerate to much higher energy particles. And with this machine, a top quark was discovered at the D0 experiment. And there were Indian participants in the experiments also. And in the LEP also, Indian participants were there in the experiments, which I talked about. And in the D0 experiment also, Indian participation was there. Several groups were there from different labs. And the final, the largest machine that we know of today, particle accelerator, is the Large Hadron Collider, which is housed in the same tunnel which has housed the earlier Large Electron Positron Collider, same 26.7 kilometers. So all the earlier machine parts were taken out, and the new freshly built magnets and the superconducting and the cavities, they're all put in. And in fact, in that there is India contributed to not only to the detectors but also to the machine. In fact, we supplied $35 million worth of $35 to $40 million worth of instruments, which included these 50,000 of high precision jacks, on which these you can see the entire machine is resting. These are about 50 micron level precision jacks, which are all these red ones, which are built by a company of Sarala near Bangalore. And these are the for the stability of the power supplies and safety checks. These instruments were built by a group headed by RRCAT, and they also built the sextupole, decapole, and octupole corrector magnets for the beams for the entire machine. These were supplied from India. And for that, we got the observer status of CERN, which now has been converted into associate membership of CERN. Now, in the experimental side, also India participated in this CMS project, CMS detector system, the central muon detector, and with this, the famous Higgs boson was discovered. The LHC was built for actually looking for Higgs, and they found it. This was, and the François Engelhardt and Peter Higgs were given the Nobel Prize for that, because they couldn't probably think of giving the Nobel Prize to any of the experimenters, because there are almost 6,000 people involved in the experiment. Sorry. The other part of the so far we are talking about proton-proton collisions or electron-positron collisions, small particles, but you can collide big nuclei also, nuclei on each other, and this has been there are two places where it has been done. Has been done so far. This is the relativistic heavy ion collider at Brookhaven National Laboratory, where again India was a participant. India had a good presence in one of the star detector, which was there for looking for signals from these collisions. And the other one is the next one is the LHC. At the LHC, there is an experiment called ALICE, which is also looking for these heavy ion collisions. And this is an event from heavy ion collisions, lead on lead, gold on gold nucleus, and you can see so many millions of tracks of particles coming out of these collisions. These are studied, and it's a kind of it's a very big project. It requires a lot of instruments and detectors of few stories high building, as big as that. And with this kind of studies, we could, in the laboratory, so far we have achieved temperatures of the order of 4 trillion degrees Kelvin, which goes to very close to about a microsecond of the Big Bang time. This is what is postulated, that temperatures of this kind, of these high temperatures were there in the universe at that time. And the recent data from the RIC analysis, as well as at LHC on lead on lead and gold proton and lead collisions, they have found that seem to have found evidence of quark gluon plasma being in the form of a liquid, more like a liquid rather than a gas. And in all of this, India is a strong participant, both in theory as well as in experiment. So we have the periodic table of the particles that we have know of today: the quarks and the leptons and the force carriers and the Higgs boson. Okay. Now, so questions still remain that we still have. Can I take another 5 minutes or so?
Okay, you can take.
Yeah. So questions remain: the limits of stability of nuclei. What are the heaviest nuclei that can exist? How are the elements from iron to uranium synthesized? because this is the, and in fact now we find what Professor Sorodeep talked about, the merger of neutron stars. In fact, neutron stars, we found evidence in the neutron star merger from the space-based telescopes of gamma rays coming out, which are indicative of the various heavy nuclei being produced in the neutron star mergers. So the other things which are of course, the particle physics are grappling with the nature of neutrinos, how many types, masses, handedness, etc. The violation of symmetries. Do quarks and leptons have a substructure? We do not know, because we don't know whether, if you go to still higher energies, if you are able to achieve higher energies, whether we will be able to see any substructure or not of such things. And then, of course, what to say about dark matter and dark energy. We know very little about them. The things are in line, which is immediately in the upgrade of LHC luminosity. That means the flux will be increased by a factor of 10, so that so improve the current and focusing. These are being done at the moment. Now upgrade work is going on, and there are plans. There are a number of plans to build a dedicated Higgs factory. That means produce Higgs bosons in large numbers. Could be a E plus E minus linear collider or a circular collider, and there are international collaboration for this for the international linear collider. India is a member of that collaboration, and there is proposals for building a higher energy 80 to 100 TeV proton collider. There is one project in proposal in CERN under consideration. The other is which China has floated that they will house it themselves. We don't know what the future will bring, but for achieving this kind of energies, what we need some technology developments. We need to develop stronger superconducting magnets but there are material limitations. Are few tens of Tesla only. Tesla is 10 to the power 4 Gauss, and at Fermilab, of course, a quadrupoles has been built with 24 Tesla per meter already. With the new types of superconductors, the high temperature superconductors have a great prospect because they can keep their superconductivity at higher magnetic fields. So people are thinking of all kinds of designs with high temperature superconductors or hybrid superconductors, etc. We need, of course, also for acceleration high gradient superconducting cavities, but then there is a limitation that voltage breakdown is in the range of 100 to 200 megavolts per meter. So if you have this kind of voltage limitation, that means you know that in a meter you can accelerate a particle to about 100 to 200, let's say 100 megavolts MeV. So if you want to go to GeV, you need about at least 10 meters. So if you want to go to 100 GeV, you need that much larger. So the 10 meters, 10 into 100. So that means a kilometer. So kilometers long. So now the accelerators becomes kilometers and tens of kilometers and so on, larger. So larger the accelerators, there's more of the real estate as well as building and everything. The cost of these things go up. Even the Large Hadron Collider was also already costing about $10 billion of that order. And the next international linear colliders are also thought to be in the ballpark of several billions of dollars, and that seems to be kind of limit that the international community is willing to put the money on such a machine. They are not willing to spend any more than that, of the order of $10 billion or so, $10 to $20 billion. So we have to keep our budget also. So that means you need better technological hold on to make the accelerators compact and still go to higher energies. So I'll not go into that. So the international linear collider, which has been already in a international collaboration of which India is a partner, and we talked about that. And it's a proposed one which was discussed in 2008. And it's waiting for the Japanese government has in principle given some kind of, they have not yet approved it, but they are encouraging their scientists. There is enough encouragement to keep thinking that it can maybe build. So there are two options now, that it could be electrons, positron go up to 500 GeV each or 250 MeV each, and it will require a huge number of such. These are the electromagnetic cavities which are now made of niobium material, which accelerate the particles as they go through it from cell to cell. They get accelerated. And the other one is increase the intensity of beam for high intensity beam, but not very large energy, not that high energy, but intense intensity to make neutron sources. There is a project at Fermilab which is called the Proton Improvement Project 2 for them, and India and a number of institutions in India are collaborating with Fermilab in this. So this will be essentially about a GeV LINAC. It's supposed to be a 3 GeV finally, but in the initial stage it will be 1 GeV, 1 to 2 GeV will be built first, depending on the money available, and then it will hit the target and produce. Finally, it will produce the neutrinos. It's basically for generating high flux of neutrinos to study the neutrino physics. So this is in there, and in that also India is collaborating. We are collaborating in the cavity, also the accelerating structure, as well as the powers. For example, the RF amplifiers have been sent from RRCAT to first batch has been already sent, and the first module of this accelerator has been successfully tested amplifiers at Fermilab in April, from last December to April this year. And these are the some pictures of the cavity accelerating structures that we developed at RRCAT and IUAC jointly developed these kind of cavities. The single cell cavity, and this is a 5-cell cavity, and then 9-cell cavity final. These ones are the ones which will be used, and the different type of cavities also here. Niobium cavity. These are all made of pure niobium material, which is a superconductor, and this has to be all be kept at 2 degrees Kelvin with liquid helium, pumped liquid helium, so that the resistance is very low, and then well, it's not just to remind you that this is in the RF resistance, and the RF resistance is not zero for the superconductors. There is a BCS level cutoff, so it is a few nano ohm, but it's small, but it's still finite. So with that, so the idea of these cavities is that you can put in very small amount of power and get a very large magnetic field. So magnetic fields, for example, in our cavity which we made first was about 35 or so megavolts per meter, and the acceptance level for the ILC as well as the Fermilab was about 31 megavolts per meter. So it all crossed that barrier, and it is it has been accepted by the Fermilab collaboration. These kind of things, international collaboration has accepted this kind of cavities. So we have accelerator program in India, radioactive, and there is in the country we have some smaller accelerator systems, smaller but nevertheless extremely important and high technology challenges. There's to produce radioactive ion beams at VECC, the spallation neutron source at RRCAT. This will also involve our high intensity proton machine like that in Fermilab, and that is one of the reasons why we collaborated with them. So that technology collaboration will help us in building our neutron source. Spallation is over 1 GeV protons, very high. And it will also help us in our accelerator-driven subcritical systems at BARC. There are, of course, free electron lasers being built at RRCAT and IUAC. And international projects, we are participating in the Tesla International Linear Collider collaboration with Fermilab for high intensity protons, and also we are in the FAIR project, which is a heavy ion accelerator project in Germany, Darmstadt, which is actually on, and it will start probably functioning another 2 years time. 25 it's supposed to be completed in 4 years time. The first beam will be available about 2 years, and it will be in multidisciplinary physics, from atomic physics to plasma physics to nuclear physics to for particle physics. For high energy physicists, the thing of interest would be the compressed baryon matter experiment with the high energy heavy ions bombarding each other with very high intensity. So you can study the matter at high density. Well, just I think I'll skip that. All these technology boosts that we get from making the accelerators, apart from making came actually from the fundamental for the quest of structure of matter, understanding the structure of matter. But there's several technologies got built on the way, and this has all found applications in the societal benefits. There are many of them. I'll show you only a collage of pictures, nothing else. And only one point I just want to make for high energy, that it can be high energy proton accelerators that we can make can help us reducing the fission waste products from fission. If we combine a accelerator, 1 GeV proton accelerator with a subcritical reactor, and then the proton beam comes in, generates lots of neutrons here, makes the reactor go critical, and then you can switch off the proton beam and the reactor will shut down. But in the process, when this large number of neutrons, high energy neutrons are present, it will not only the fission process, the products, the actinide especially, will get converted into very short lifetime of radioactivity. So this is one paper from Robert Klapisch, which he published, that if you make let's say a reactor which is there, and the radioactivity, so let's say, starts with you shut off the reactor, the waste products decays like this, decays very slowly over thousand years or so. Whereas if you had used this energy, the ADS scheme, accelerator driven subcritical system, put the high energy proton accelerator to generate the neutrons, within a few, the activity, the toxicity of the radioactive waste is reduced so much that the decay takes place, and it comes to almost the natural level in few hundred years time. So keeping the waste safe for few hundred years is quite feasible, and we know the many geological structures which are stable over 1,000 years, and we can surely do that. So it'll be a good solution for the waste disposal problem of fission reactors. So I just close with this slide, which is for societal benefits. We have from the accelerator, the technology that has come out has impacted making better heart valves, which can be more biologically adapted in the body. We can have medical supplies are all sterilized by electron linacs these days. The baby's diapers are made softer because you can change the cross-linking of polymers by energetic ion beams. And you can look at, of course, synchrotron radiation looks at the protein structure. In fact, this is the structure of the spike protein of the coronavirus, which helped in making the vaccines suitable to this, to neutralize these things. And it can be used, it is used for art objects, age determination, that is the mass spectrometry, accelerator mass spectrometry. Then it is used for therapy. Electron linacs are used for therapy, and for electron linacs are used for cargo inspection, for safety and security purposes, and also for food preservation. So these are just only a collage, but there are many others which I will not, which will be another lecture. It has to be if you want to go for the applications. So this, as you've seen, that the accelerators, as I told you, accelerator kept pace. Energies have kept pace with the quest for structure of matter. We have solved the challenges have been met, and so far has been successful in fueling more and more deeper in understanding and in theoretical understanding also. And it has both experimental and theory has gone hand in hand with the help of accelerators. Application in other science areas, the quest continues, and many challenges ahead for the future researchers. Thank you very much for the patient hearing.
Let us thank Professor Roy for his wonderful talk. Now, accelerating particle from KeV to TeV, and from international scenario to Indian scenario. So, any question from the audience?
Can I ask something?
Sure.
Yes,
Professor Roy, beautiful talk and very nice history you have presented. So thank you very much. I have a question which is slightly unrelated, but since it's a Foundation Day talk, I think I can ask this. So, what I found in this talk, okay, I would like you to say a few words about the missing of Nobel Prize by Madame Wu. So, because most of the history of accelerator physics, as we know, is rich with many men getting the forefront and
yes.
So, and also since you are in, I think, this something about Vibha Chaudhary all the way to our own person who is missing the Nobel Prize. Yes, please.
Yeah, let's see. The Madame Wu's case is is not so bad, I would say, because there have been much more stark instances where women have been ignored. For example, the prime example there are examples those of Lise Meitner, for example. I think I mean it is a travesty of the Nobel Prize not to give her the Nobel Prize. It was because it has been proved. It has been, in fact, I have written an article on fission, this history of fission in resonance, and there I have got it from these various sources. I have taken them, of course, not mine. There I have also written about it, that the Han was in communication. He was telling them, Lise Meitner, all the time what he has found, and that he doesn't understand what just happened. He correctly found that fission had taken place. That means uranium was broken, but he didn't understand the process. It was Lise Meitner who gave the idea of the fission, that actually it is fission. And she showed it, that the first paper in Nature with Otto Frisch, her nephew, they wrote together, which showed that this is a fission event. And she was ignored for that. The Jocelyn Bell's case for pulsar also is a travesty of justice, because she is the one who found the pulsar, and Anthony Hewish got the credit. But Madame Wu's case, it's not so bad, because there has been recently an article by, in fact, Ruth Syme. She writes on these things. She also another lady whose name I forget, who has also written about Madame Wu. See, Madame Wu's case, there is a little bit. It's in the borderline case, I would say. Actually, when the K-meson thing came up, the anomaly in the K-meson 2 pi and 3 pi decay, the parity, and Li and Yang suggested, they came to the conclusion that parity is violated. And so they're looking for examples. And in fact, in their paper, they write about 3 examples where it can be tested. One is the meson decay, other is the beta decay in 60 cobalt. Now, that idea came from Madame Wu. In fact, this is not published, but this was later on, it has been different. In some cases, it's been told orally, and other there are some documentation that Liu and Yang, when they came to Madame Wu, immediately said that the parity, because they knew that she is an expert in this beta decay. So they talked to her, and the Madame Wu suggested that cobalt 60 would be the right choice, because she knew about the properties of cobalt 60, that it has a decay, that delta T equal to 1 decay, etc. The isospin change and so on, which is a favorable case for the looking for the polarization of beta decay electrons. And so this was included in their paper, Lise and Young's paper, as one of the examples. Now the problem that with Madame Wu's case was that in the similar within the same time, at the time they published the paper, this beta decay, it took a long time, because they had to orient the nuclei and all those things. The big story. And similar, the Lederman and Garwin, they learned about this, that the beta parity thing is going on. So they immediately, the meson, they also did the experiment, and their result was published simultaneously, all one next to each other in Physical Review Letters. Madame Wu's experiment as well as the Garwin Lederman's experiment. And then there was another experiment at the same time, within a month. It was going on for some time by a group in Chicago, which also found the mesonic, the decay, the parity violation meson decay. So I think from the experimental side, the Nobel Committee must have been in a fix, because they could give the Nobel Prize can be given only to 3 people maximum. That's
But
the convention.
From what I remember, she was nominated several times.
Oh yes.
So
She was nominated several times, but this was for BJDK part has already been given. Parity violation has already been awarded case, so these are not considered. But she was considered as one of the top leading experimentalists in USA, and she got the Fermi Award of US. She was elected immediately to the APS. After her BJDK, so she got enough. She herself never had any problems with the not getting the Nobel Prize. That's what I learned from looking at her life history, which I studied.
Okay. And any words about Bibha Chaudhary you want to?
Bibha Chaudhary's case is it's a very unfortunate case again, because that was actually I don't think that Bibha Chaudhary actually deserved the Nobel Prize in that sense, but her experiment, which is did with the what is that called? It's a plates, photographic plate, emulsion, the emulsions which they took at Darjeeling, Sandak Fu. They exposed it and then looked at the meson. Now they identified the meson all right, but the problem is that their plate thickness was small, so they could not find the full energy. They could not give the mass they gave was about the order of 200 electron mass, which everybody thought it was like the muon mass. Muon was about that 110, it was 105 electron mass. So that was not the thing. But then Bibha Chaudhary at that time was in Bose Institute, and then she left, and then in the 45 or so she went to Birmingham in Blackett's lab. In Blackett's lab, Powell was working also in Blackett's lab, and so obviously they must have discussed. And in fact, to be fair to Powell, in his Nobel lecture, he mentions that they use the technique of the energy determination of Bibha Chaudhary from photographic emulsions, that density method. Bibha Chaudhary and D.M. Bose, in their paper, they have written how to get the mass out of the tracks. The energy determination from the tracks. So the methodology was Bibha Chaudhary's, but then the actual discovery was not hers, because they didn't have thick enough emulsion. Whereas Powell, being in England, he could get the thick enough emulsion from the Kodaks, and then with that he found the tracks, full track.
Okay. Thank you.
Any other question?
Yeah, Sanjeev.
I just want to add, Professor Roy, when you mentioned about Professor Wu's contribution, actually, I read the nuts and bolts from your one pedagogical article you wrote on parity violation, which I always recommend to my students to read, and where you you explained that Wu's contribution was that interesting choice of cobalt-60. I think that was amazing. That she had that knack, because they wrote the letter to Madame Wu, Professor Wu, right? Why don't you just look for this? And she immediately took up, out of all possibilities, cobalt-60, and which was like, you can really orient the nucleus. Basically.
Yes. So
I think that her cleverness was in picking up the right material, because she had the experimental training. So, and in your article, you explained that, where exactly her charisma comes in proving this particular phenomena. So I just wanted to make a comment, basically. That's just choice was very interesting.
That's right.
That's right. Yeah.
Actually, what is the status of Indian point of view? Because you told only four accelerators are listed, I think. And what type of experiment they are doing?
Yes, I didn't go into the experiments that much because we are mainly going into right now for Indian researchers in nuclear physics. With the accelerators that we have, the type of experiments that are going on are in materials, study of materials and condensed matter with the low energy machines. You can do, as I said, focused ion beams with the make nanostructures and so on, and study them. You can generate different kinds of structure inside. You can make you can study the movement of ions, and then for tracks which can be used for pinning centers, etc. This was one of the good work that came out of IUAC, that high energy pelletron machine in material science, that the flux spinning or in these high TC superconductors through this ion bombardment. That was one of the good things that came out. So these similar type of studies are being done. And then nuclear physics, of course, low energy nuclear physics, entire structure and dynamics, nuclear reaction dynamics work is going on in the centers in India.
How they are used in biology, basically, in agriculture?
In biology directly, well, I didn't talk about that. It's in food, for example, the food preservation. Yeah. That the linear accelerators are being used now in number of places in India. In Navi Bombay, there is one center which is doing it regularly. There is Indore, they have set up, and near the Sabji Mandi, they have set up a accelerator-based irradiation facility. And there are other places, for example, groundnuts, which are used in Maharashtra and Gujarat, which are being actually cultivated, are irradiated groundnuts.
For this, how much energy you need actually?
For that, it's not very much. It's about 10 MeV Linacs. Only 10 MeV electrons that is required to produce the X-rays. That is what is used. Or directly electron, you can use electron bombardment also of the order of 10 MeV. And which is not very big. I mean, it's only a couple of meters long accelerator. So it's in a small room, it can be housed. And these are the ones which are used also for security purposes, for scanning of cargo and so on.
Any other question by anybody?
My question was related to that also, what Professor Patra asked. So what is actually now the accelerator physics in India actually going on? New facilities, basically, because whatever you mentioned, whatever the old VCC, other CAT and other places, that's what all Indians are going to mega science like LSC or Star, Vinel, whatever may be. But what is, like you mentioned also, the China also trying to build the high energy accelerator also.
Yes.
So what is the contribution for India side, recent one?
You see, for making in India, the bigger accelerators for particles, which are useful for particles, GeV range is a very big machine, and that cannot be that will be a lot of money, and I don't think the government is willing to spend that kind of money for building. Again, repeating,
not only
but already
GeV, not only for GeV, for any accelerator have we made?
Yes, we have made our accelerator is, for example, both in TIFR as well and BRC, the linear accelerator part is made in the country.
No, that is actually what existing, but what is new accelerator is planning?
Planning, that is radioactive ion beam facility at VCC.
VCC, yeah, that I know that. But now
that is the one. That is one.
Collaborated one accelerator, and now see, like IOP has one very old one that has to be upgraded, or any such type of planning there.
Dr. Sahu, the thing is, I told you, the radioactive ion beam facility is a new facility at Rajarhat campus, not in old VCC campus. It's being built. That is not yet built.
Okay.
That is going on. It's right now ongoing project, which will be taking another 5 to 6 years to build, complete it. So that will produce radioactive ions which can be re-accelerated, which will be re-accelerated and then studied. So that is one of the projects, which is the radioactive ion beam is a facility, is the one which for nuclear physics, that is the way to go. And all the other countries in the world, they are doing that. All small facilities have been shut down. They are now using for something else rather than doing basic nuclear physics. Only now in USA, for example, they are concentrating on the radioactive ion beam facility in Michigan State University, which is just getting completed. It's not yet complete. It will be complete in another 2 years. So they started preliminary experiments at Michigan. There is one center in the whole of US. There is one center in the whole of Europe, that is in Darmstadt, GSI, and there is another one which is in Caen in France. That is also running. That is also radioactive ion beam facility. In Russia, there is only one facility in Dubna,
Yes.
and then one facility working in Japan. That is the Riken.
Riken, yes.
And China has built in Lanzhou. They are about to They are about to start that facility.
Not yet started. Yeah.
Not yet started. So these are the only facilities in the whole world for nuclear.
But in India, you have only this one RBI.
On the RBI and VCC, because again, there's no point in making number of them. It's very costly. So we can only have one of a kind. The other accelerators which are being built in the country are the ones for application purposes, not for nuclear physics. That is for neutron generation. The RRCAT has a project for making a 1 GeV proton accelerator, which will be high power, 1 milliampere, so that it can produce large number of neutrons for material science and the condensed matter research. So neutron, that is one project which is going on. And the BRC also has a project of the similar type for the energy purpose. I say accelerator-driven subcritical systems.
Okay, but whatever the existing one, is there in plan like to upgrade that one or?
Right now, I don't know of any upgrade plan of the existing apart from the VCC. That superconducting cyclotron is the only that is already there. Yeah. The IUSC also doesn't have any other further plan of upgrade. There is a little, yes, there is a small plan which is going there. They will only increase the number of ion species. That means a small accelerator, high current injector is being put for the linear accelerator. Linear accelerator that we built. So another injector is being built for which will make the flux higher. Intensity will go up so that you can study reactions of low cross sections, which are not possible today. So that is one upgrade which is going on in IUSC. And TIFR, there is no further upgrade of the machine. The IUSC, there is another line of has been opened up, that is for making a free electron laser. That means you make a small electron machine, not very large, only few tens of MeVs, 30-40 MeV, then put it through a magnetic field, undulating magnetic field. It will produce laser-like light, and you can change the frequency by changing the MeV energy. So first it will be terahertz will be generated. This project is there in one in IUSC, one in RRCAT, terahertz generation. So with that you can do lots of studies, terahertz studies. Then if money is more money is available, then you can increase the energy and then go to higher frequency. That means you can generate X-rays and so on.
Okay, Suresh, a small comment and confirmation from Professor Roy. I think Isolde at CERN is probably the most productive RIB facility as of now. I mean, in terms of doing physics and materials research and all this, correct?
Yes, Isolde is, of course, have been running for a very long time. And it has they have changed slightly more the configuration, and now it is having a radioactive ion beam accelerator also.
Okay, thank you.
May I make some comment, Professor Patra?
Sure.
Yeah. So, Professor Roy, while you are answering the questions by Dr. Sahu, I would like to add that building a accelerator of new kind from scratch in the country, that has to be debated, because we need to see the global avenue that where we can contribute and something will be new. There is nothing.
Sorry, I did not ask that one.
No. Let me just finish. What I want to just comment, that we need to see that where we are contributing, and I would like to mention one avenue, the Project X planning in Fermilab, because we know that Fermilab's future is totally devoted to neutrino science. And there is the one experiment, deep underground neutrino experiment, DUNE.
Yes.
And they need a completely new beam line and a huge, highly intense neutrino beam, which they will produce by hitting proton on a target. And I am very happy to see the Indian contribution in the development of that beam line. There are many places where RRCAT, Indore, and maybe Professor Kanjilar, he would have been here, he could have mentioned more. In this whole planning of Project X, India's contribution is enormous.
Yes. Actually, the thing is that Indian contribution is everywhere is high. Even now, also in the LSC, Indian contribution quite a lot. But somehow our government is not encouraging.
No. I think I have a different take. It's all right. It's okay. We like Professor Sauradeep also said that we are encouraging. Now we have been increasing some mega projects. We are participating. But again, see, there also the LIGO project is not completely ours. It is actually US project. So we are building one leg of it. But the idea of this is, building something on your own soil has the advantage that some of the technologies you have yourself.
Yeah.
And that technology can be transferred to the industry. For example, in our case also, the cavities and all that thing, we have given it to there are outside companies which can make it. Our high vacuum chambers, they're made in different industries. So, I mean, for example, in vacuum technique in Bangalore, we were the first in from IUSC to give them a chamber for making a cryostat, large cryostat of 1 meter diameter, 2 meter tall cryostat. And after that, they completed that. They got several orders. Not only that, some of their vacuum components now they are exporting to US, UAE, into Canada. So,
Yes.
This kind of transfer has been taking place. So this is the gain that the country gets. But of course, I also agree with Sanjeev that we cannot build everything, because we have to choose our mega science budget basket is there. We have to choose very judiciously what we pick up, and some of the things we build, some we collaborate.
Yes. So that is, I see that India became the membership of to its CERN.
Yeah.
So that is why the technology can be transferred. And
That's right.
I think
Exactly.
why actually now this gem detector has been built in Bangalore.
Yes, I know it's built. Yeah, sure. We are doing that.
So
and that gem detector technology can be used in imaging everywhere.
Yes, imaging and particle detector, all sort of things.
Sure.
Yeah.
Actually, I must say that we should look at the positive sides. If we just count bit by bit what has been done in last 15-20 years in our country in this direction, things are very encouraging, I must say. But only thing I think we are lacking is the training and the creating the environment of experiments from the very childhood level. The encouragement towards experiment from school, college, and university.
No, Sanjeev Babu,
that's why we are not coming into the limelight.
Don't think that people are
No, this is a debate which will go on for a long time. No, actually, let me point out one thing. See, we in fact we did something in that direction about the helping the getting some affordable instrument for doing experiments in the laboratories in the undergraduate and a postgraduate level. We did that. See, there is a project we took up about 2003. We started there in IUSC. Is called the Phoenix experiment. It is called it was Phoenix first name. It is called now EXPEYS. And there, my colleague, he developed a small box which consists of lots of electronics cards built in, miniaturized now. Earlier it was in big cards, it was now miniaturized, and these are entire from the detector to the computer, the entire electronics is replicated, which electronics which used to cost about 5 lakhs rupees is replicated by a small box which is only 3,000 rupees.
Yeah, this is a prototype of 10 things.
This has been done, and this has been used now. We have given it. It has been now many ISARs are using this for the experiments. For doing the experiments.
So we can get one at
IOP? Surely you can contact.
Because we have a pre-doc course for 1 year, and
definitely
we can add to our experimental training.
Definitely, we can get it.
Sanjeev, a small comment. When
actually I wanted to say
director at IUSC, okay, he was kind enough to donate when I requested him to donate 2 alpha spectrums to be set up, which had been long used by our pre-doc scholars. Once again, thanks, Aminda, for that one.
I think that's correct. Yeah, we should.
But Kapota, now what Professor Roy is telling, can we grab that opportunity? Because
anytime.
Yeah, you can certainly.
Don't worry.
You want to tell something?
Yeah, I think I'm very good to see Professor Amit Rai after a long time and online. And I don't think 20 years have passed almost, but there's no change in you. It's very nice to see that. So energetic and other thing. The academic side, I think many young people like Sanjeev, other things, probably they do not know certain things. That's really, for example, Ajit Kumar, whatever he has made, there are predoctoral experiments. Of course, while I was there in IOP, we are still using them. We have Phoenix box. We have all these boxes still available there in the IOP lab itself, predoctoral lab. Probably he doesn't know that one. That's the thing. So several things have been procured from Ajit as well. So that is one thing. But what I feel is that this is probably one of the very comprehensive talk right from the discovery to the next 20 years, what we are going to do. I think I've never heard that kind of a comprehensive talk. So we must admire, and I think fortunate to have you for this foundation.
Thank you very much, Satyam.
So the other points, maybe small remarks, is that, I see that 15, 20 years back, maybe I moved to electron microscopy. Maybe I may be missing something. Tapo can comment on it, Shikant Tapo. But I feel that there is a lull in the sense somebody is talking about experimentation in the accelerators at other than IUAC. That has gone down. I mean, there was a bubbling nature 10, 15 years back. Now suddenly we see, and now the new technologies comes up, ADS, of course, free electron laser has already become old. Probably because many other place lacks and everything, they have electron laser. We are again lag behind thanks to IUAC. At least we are in the some part of it. So there is a difference. I think my feeling is accelerator training or accelerator participation, which IUP used to play a lot at that time. Probably it can be, overall India, there can be something can be brought back with the newer technologies like ADS and other things.
That's true. In fact, having an accelerator running and getting students hands-on experience in accelerators gives them training in number of techniques like vacuum technique, high voltage, then low temperatures. So they handle so many things, control systems, computers, of course.
They build foundations, actually.
Yeah, it's a very good foundation. Electronics. So it's a kind of broad-based experimental for experimentation for in an accelerator lab. That's the best place for training an experimenter.
Okay,
thank you, Amit. Thank you,
Professor Roy. We are very much thankful to you because you give time and speak so much thing. We learn many things. Although we are learning many things from you, today also we learn so many things. And let us thanks again. And I think.
Thank you.
Okay.
Namaskar.
Okay, next we'll come at 2:30, and now we have a lunch break, and I think we close this session. Right.
Before that, I mean, Dr. Roy, if you could manage some time for the second session, talks by Professor Pinaki Majumdar and Professor Gautam Bhattacharya, who will be privileged to have you also with us.
I think he left already.
Okay.
Thank you, Tapoda. Thank you, Professor Patra, for arranging this session.
Thanks.
You are welcome.
Bye.
Sorry. Also, before you comment, you please check it up.
What?
Because we have several boxes. What he has talked about, Ajit Kumar developed things. There are several things are there in IOP.
And Satyam forget actually.
No.
I was talking about that.
They were all lab automation projects. Those experiments are got from the
IUAC from him actually.
No, Satyam, I was talking about the new thing that he mentioned. That he
yes, that's the only thing I am also talking.
Sanjay Babu, actually, when we joined PhD, at that time there was no accelerator in India. Almost it was just coming. Either it was in the
starting.
No. I was telling that if we can get one sample for our pre-doc that they have given to ISA recently.
Not a problem. It's free to give.
No, I'm saying it's already there. Right now it is there.
That is very old. So I was telling that if we can get one now.
You have to grasp. You have to get it.
Yeah, and it is not expensive.
Thank you, Professor Patro. Thank you.
Okay, boss.
But is it a part of our pre-doc course still?
Sanjeev, that you people can better because you are academic affairs committee members. Okay. You are all academic affairs.
Are you making the experimentalist?
Doesn't matter. Okay. Whether it's a part of the syllabus or not, only you people can tell us.
We are Buddha.
Nonetheless, in a lighter note. Okay. Thank you.
Yeah, no. Session is closed already. Whatever you can tell right now. Session is closed long back.
Okay.
We'll see at 2:30 then.
Good afternoon, Professor Majumdar. Ajit here. Are you muted?
Can you hear me now?
Yeah, I can hear you. Very nice. Well, thank you for joining us.
Yeah.
Very nice to see you.
Yes. Can I test out my slides to make sure things
please.
work?
Sure. Please go ahead.
How to do that on Google Meet? I mean, what is the method?
Share your slides.
There is a share somewhere. Let me see.
Present now button. There is a present now.
Present now. Let me see.
Arrow, the upper arrow. In the bottom, there is an arrow here.
Achha, theek hai. Okay, present now. A window. Okay. Fine. Let's see something else.
Yeah, you can put it full screen now.
Yeah, let us get to. Okay.
Yeah, good.
This is full screen now?
Yeah, full screen. You can change this. It's fine. It's changing.
Yeah, just go to and keep it on the first.
Okay, good.
Okay.
Sure. We'll start in about a minute.
Yeah, you let me know when to start. I'll be around.
Sure.
Take it.
Hello, Professor Majumdar. This is Shikha.
Hello.
Hello, how are you?
Aha. I hope we could have gotten together. I mean, this is
Yeah.
this will be a foundation. Anyway.
I don't like online talks anymore. Yeah.
So, how is Orissa improving in terms of COVID, or what's the situation?
It is improving. They are doing good control here. I'm surprised.
You have good control there.
Yeah, I mean, they don't. For example, they don't allow people out on major festivals. That's Yatra, the most important festival of Orissa, and they had a strict lockdown. So I think they have managed quite well here, actually. I think.
Okay. So your students are back on campus?
Yeah.
They are.
Students are back on. How about HRI?
Yeah. I mean, look, we don't have labs, so people can work from their rooms also if they want. So,
right, but they are on the campus. But they are back on campus.
90% of them are on campus.
All right. Great. How is the situation in Allahabad, by the way?
Oh, I think UP, I mean, for miraculous reasons, seems to have done quite well. And the numbers are 1s and 2s at Allahabad, the daily numbers. So it's under control.
You trust your numbers here?
No, we don't. But the point is, if you look at hospitalization and death, those are better indicators. They also seem to be on the lower side.
I think it's lowering everywhere actually now.
Yeah.
But after that disaster of April, May, it's lowering everywhere. Those were frightening periods.
Yeah. It just burned through. I mean,
burned through. It was like wildfire through the country, across the country. Yeah. Correct word you use. Suresh, shall we start? Suresh Patra, Professor Patra. Hello, Suresh.
I suppose Suresh got disconnected. So I think we can start. We can start.
Okay, right, good. So, Professor Majumdar will start now. Huh?
Yeah.
Okay.
So do I start the talk?
No, I should.
Oh, you say something.
Yes. It's an honor for me to introduce you. So we are very happy that Professor Pinaki Majumdar has joined us for today's celebration. Professor Majumdar did his bachelor's in electrical engineering from Jadavpur University in 1986. MTech Solid State Technology, IIT Madras. I didn't know that he had an engineering background. IIT Madras in 1990. And then, like some of the engineers could switch to physics, PhD in physics, and they did extremely well after that. PhD in physics from IIT Bangalore in 1996. He was a postdoctoral fellow at Bell Labs in New Jersey, USA from 1996 to 1998. And he has been at HRI as a faculty member, Harishchandra Research Institute, Allahabad, since 1998. And as a HRI director since 2017. Professor Majumdar is also a member of our governing council. His main area of research interest is disordered and strongly correlated quantum systems, metal insulator transition, quantum magnetism, etc. Professor Majumdar is a recipient of the Global Innovator Award of the Massachusetts Institute of Technology. He was awarded the Shanti Swarup Bhatnagar Prize in 2007. He is a fellow of the National Academy of Sciences of India. And we are very indeed grateful to him that he is with us today on this, the most important day of our institute. So I now request Professor Majumdar to deliver his talk.
Thank you, Ajit. I can see that Professor Nanda has set a tough schedule for the Foundation Day. I mean, there are 4 technical talks. Difficult going. I mean, I thought on Foundation's Day you get together, have lunch, play cricket, etc. But this is serious stuff. So the formal title of my talk is A Classical Approach to Quantum Many-Body Theory. Now, this may sound intimidating. And the more frivolous title is sort of Langevin in Quantum Land, which borrows from George Gamo's Pumpkins in Wonderland. It's ultimately, after all the sort of heavy stuff has vanished from the screen, it's an attempt to relate a stochastic method developed in the early 20th century to attempts to do many-body theory today, quantum many-body theory today. So the classical physics of a single particle, or the attempt to relate the classical physics of a single particle in a stochastic environment to that of phase transitions, ordering, etc. in quantum many-body systems. Let's see how well things work out. So the outline is to give you 2 slides on the original Langevin equation, should be known to most physics people. Then shift gear completely and jump into quantum many-body physics, seemingly unrelated in any way to what Langevin had done. So sections 2, 3, and 4 basically look at the whys and hows of many-body physics within the limits of the time that we have. And basically inch towards a classical or semi-classical approach to quantum many-body theory. May sound mysterious right now, we will see how things pan out. In number 5, I bring up one of the sort of key problems in interacting quantum systems, the so-called Mott insulator, to understand which you essentially have to invoke interactions. Band theory doesn't predict a Mott insulator. And C, or use it as a testing ground for understanding how this classical, semi-classical approaches, including a reinvented Langevin approach, makes some sense or provides some information. Then I conclude. So first, the Langevin equation. So in 1908, 3 years after Einstein's work on Brownian motion, Paul Langevin wrote down a quantitative description of Brownian motion. And that goes by the name of the Langevin equation right now. The upper panel is a Wikipedia picture of a particle executing Brownian motion. This is typically a pollen grain in a fluid at finite temperature being kicked around by the water molecules and shows a very jagged random walk kind of pattern. So what Langevin wrote down was a generalization of a Newton's equations. So in free space, Newton's equations would be just sort of m dv dt equal to 0. He augmented it by putting in a dissipation coefficient coming from the drag induced by the fluid and a random force because the fluid molecules are kicking that target particle from all directions. So gamma is dissipation, eta is fluctuation, and in fact, gamma and eta are related by what's called the fluctuation dissipation relationship, which is this eta alpha, eta beta, blah, blah correlator down there. So the mean value of the noise is 0 because there is no drift in any direction in this problem. I mean, on an average, you are in the same position, although the cloud is diffusing outward. And 2, the strength of the noise is basically 2 gamma kt. Now, why is it 2 gamma kt? Because at long times you want it to satisfy the Boltzmann distribution, equipartition theorem, etc., etc. Now, this was a free particle. You can look at more interesting examples where there is a potential brought into the problem. So there is gravity, there is a harmonic binding, etc., etc. And then the right-hand side is just augmented by a systematic force. So m dv dt has friction and noise as well as a force, which is the gradient of the potential. What is the outcome? Detailed solution apart, what one can demonstrate is, as t goes to infinity, the long-time distribution of R and V is just the Boltzmann distribution. Okay. Looks a bit magical, but can be demonstrated using what's called a Fokker-Planck approach to the problem. Now, if I just wanted a Boltzmann distribution, why all this song and dance about writing dynamics? Okay, so if you're just interested in thermodynamic properties, all this Langevin business is irrelevant. But if you're also interested in the nature of dynamical fluctuations, the power spectrum of fluctuations, or you want to understand the approach to equilibrium, not just equilibrium itself, then the dynamical approach is essential. So the partition function computation or configuration sampling is an approach that gives you only static or what I'll call thermodynamic properties, while the dynamical approach embodied in the Lagrange equation also gives you information on spectral features and potentially the approach to equilibrium, out of equilibrium phenomena. Now, these are two self-contained slides. What does any of this have to do with many-body physics? Okay. So to summarize this broadly, for complex systems, for one single particle, things are trivial. We do it in sort of our BSc, MSc classes. For complicated systems, statistical mechanics, either samples or a theorist either samples configurations or does stochastic dynamics as in the Lagrange equation. And my sort of proposition is the second approach is more powerful and gives you more information than the first one. What does it have to do with many-body physics? Okay. So a bit of schoolboyish pictures on many-body physics. So many-body physics is at the heart of all the spatial organization you see in nature. Matter holds together because there are intermolecular, interparticle forces, ranging from the scale of galaxies to liquids to nuclear matter, sort of cosmic to subatomic scales. Interactions are vital, and you need to understand different versions of the many-body problem. What are the interesting problems in quantum many-body problems, leaving galaxies, etc., out for the time being? Well, if you're a high-energy person, the quark-gluon problem is a typical strong interacting phenomenon. If you're a low-energy person looking at condensed matter, then the old many-body problems related to the quantum liquids, helium-3, helium-4, the difficult problems on which sort of Onsager, Feynman, Landau spend their time. More contemporary, over the last 30 years, the focus has been on correlated electrons in solids, in so-called oxides, actinides, lanthanides, etc., which are d and def electron systems with small bandwidth, with the relative strength of electron-electron interaction to kinetic energy is a large number. What do they bring up? 3 random examples from the past 30 years, 40 years maybe, if you look at high TC. So the left-hand example is that of high TC superconductivity discovered in the cuprates in the 1980s by these two gentlemen, Bednorz and Muller. And it has turned out that quite beyond the high TC superconductivity in a doped insulator, which itself is remarkable, there are many other features which are striking and have no parallel in the band theory of metals. You get metallic resistivities which are linear in temperature, you get what is called a pseudo gap, you get charge ordered stripes, etc., etc. And none of this would have been anticipated within a weak coupling or free electron theory of metals. So that's the left panel. The central panel is sort of an artificial object, a low density electron gas in a semiconductor subject to a large magnetic field. You get the fractional quantum Hall effect. The integer quantum Hall effect is readily understandable in terms of Landau quantization. The fractional Hall effect is not, and you have to invoke correlations between electrons to understand the Plato structure below nu equal to 1. This is not a typical solid-state material. It's an engineered system, but demonstrating the impact of electron-electron interactions. The right-hand side is another material. The left-hand side is a cuprate. The right-hand side is a manganese, a copper oxide and a manganese oxide. And while the left-hand object demonstrates high temperature superconductivity, the right-hand object goes by the sort of abbreviation of CMR, colossal magnetic resistance, shows you sort of a 99% suppression of resistance, striking, on application of a modest magnetic field in a ferromagnetic metal. So there are actually, you can actually convert an insulator with a potentially diverging resistivity into a metal by applying a reasonably small magnetic field. So the key figure in that field is someone called Yoshinari Tokuro. So these are materials sensitive to small changes in doping, temperature, or applied field. Are we supposed to be surprised? Well, what would have happened if you look at the textbook free electron system? I guess there will be some students in your audience. So if you look at the free electron theory, the only relevant scale in the problem is the Fermi energy. And if you change carrier density, change temperature, nothing happens till you're at a temperature scale kT of order EF, which is thousands of Kelvin, where you basically get a quantum to classical crossover. So this is a boring phase diagram. On the space of density and temperature, the free electron gas does basically nothing. Okay. And by the time you go to KT of order EF, the object has melted. What happens in correlated materials? I showed you 3 random plots on phase diagrams here and there. Let me show a slightly more organized picture lifted from a review by Elvio Dagotto, which shows in a wide family of primarily oxides. Okay. The top left is a manganese oxide, then the right-hand side after that is a copper oxide, then there is a ruthenium oxide, etc., etc. Are we supposed to focus too much on the inner details? What you see is in contrast to a free electron system where I get a bland band metal, featureless, and maybe with weak interactions treated perturbatively, you see a plethora of phases. The various colors represent ferrometal, antiferroinsulator, charge ordering, superconductivity, and what have you, non-Fermi liquids. Many of them with their own interesting transport features. Some are good thermoelectric materials, others are superconductors, highly magnetoresistive. So small variations in carrier density, temperature, applied magnetic field lead to dramatic changes in the underlying phases and in the physical response of the materials. So there are finely balanced phases close by in energy, living in proximity in the phase diagram, and you can go from one to the other by tuning a small number. So the very existence of these phases is arising out of interaction effects. They would never have arisen in a free electron system or a band electron system. And the sharp jump from A to B to C indicates that the energies are actually very closely balanced. It's also the basis of technological use because you would want to change the phase of matter by applying a small temperature, okay, a modest increase in temperature to switch something, or a magnetic field probably in the milliteslas, rather than having to use fields which are hundreds of teslas or temperatures which go into thousands of Kelvin. These are materials which demonstrate these variety of phases and tunability of the transition. So there is competing order and phase transitions in these interacting electron systems. What would we like to understand in this? Well, I mean, a theorist and an experimenter would want to understand the low temperature state, which is the ground state. What kind of order does it embody? The nature of excitations on those, because they dictate scattering, specific heat resistivity, etc., etc. The response to applied perturbations like electric and magnetic fields, light shown on the material. For example, qualitative questions is, how does superconductivity arise on doping an insulator? Doping a Mott insulator, in particular, when you look at the high temperature superconductors. This is a question people have been grappling with for the last 30 years without any conclusive answer. We have proceeded a long distance in terms of discovering more and more materials which demonstrate superconductivity on doping insulators with temperatures now reaching 150, 200 Kelvin, but we're still far from a conclusive theory. How can a magnetic field decrease resistance tenfold? We have had more luck in understanding this. So the cuprate problem, I would say, is unsolved. The manganite problem, the manganese oxide CMR problem, is somewhat better understood. So why are these problems difficult? Why don't you understand everything involved in the phase diagrams I showed you in the last page? Well, this has to do with the degrees of freedom that entered the story. So all these materials, which display this exotic varied properties, involve many strongly interacting quantum degrees of freedom. And we need to understand the ground state as well as the thermal transitions. What is the degree of difficulty? I mean, it could be difficult, but how difficult? Band structure is not trivial either. So technically, if you are looking to compute thermal properties, you need to understand the StatMech, the partition function of the system. The size, quote unquote, of the Hamiltonian defining these problems is exponential in the number of degrees of freedom, number of sites, number of electrons. I'm not getting into the finer details of this. So if n is the number of electrons involved, or n is the number of lattice sites you're considering, then the Hamiltonian is non-factorizable. You cannot say, oh, it's a product of single electron problems. It is not. It is an essentially entangled many electron problem. And if n is 20, e to the 20 times e to the 20 problem, way beyond the reach, forget analytical solutions, even the numerics becomes daunting. So a brute force approach doesn't look very tractable for meaningfully large n. I don't want to understand two sites. I want to understand a cluster and maybe something large enough to mimic a solid so that I can make predictions about its properties. So how does theory usually proceed? Let me give you the toolbox. This is not a many-body course, so I'll be very telegraphic in terms of listing out A, B, and C, three methods which people have been using before sort of trying to push across my own. Okay. So, and I do it in the context of one particular model called the Hubbard model, rather than give you a general formulation of many-body theory. So look at a problem which is the simplest. This is the Ising model of many-body physics, if you wish, where particles hop from site to site, nearest neighbor. I have drawn a lattice on the right-hand side in 2 dimensions. And if you're an electron sitting on site I, you can go to I plus 1, or upward along the axis or right along the axis with an amplitude t. And if 2 particles sit on the same side, there is a repulsive cost. Now, all of this seems to be physically obvious. Electrons are Coulomb particles, so they would have a repulsion between them. And of course, they would have a kinetic energy. From an orbital in one atom, you would jump to a corresponding orbital in the next atom. Okay. So while the structure of the model is obvious, and some of the features I'll talk about are also fairly straightforward, actual solutions of this problem in the interesting parameter regime turns out to be very hard. But what is the sort of the crude physics of this? So if you look at a situation where the number of electrons is equal to the number of sites, you just sort of set the stage and be at a concrete parameter point. So I have a picture with 9 sites, 3 into 3, and suppose I have 9 electrons, or I have 16 sites, 4 by 4 and 16 electrons. When the interactions are weak, you essentially have a perturbatively renormalized free electron gas. I mean, don't be frightened with this sort of big words. You will see wave-like behavior of those electrons, mildly scattered by the interactions between them, and the presence of a Fermi sea, a Fermi gas with a Fermi surface. Propagating objects will lead to essentially good momentum eigenstates and a corresponding discontinuity in the Fermi distribution. But what if the interaction was much stronger than the kinetic scale in the problem? Without too much difficulty, you can see that in that case, the kinetic energy gets completely inhibited. Because the moment you try to jump from one side to another, and there is an electron sitting on the next side, has to be with opposite spin, you encounter a large repulsive cost. So this is, if you wish, classically you would call it a jamming transition, because there is simply no room to move to the neighboring site without sitting on top of someone else. And that sitting on top of someone else costs a large energy. The U is supposed to be large compared to the kinetic energy. So there ought to be a transition between these two states, between the U much less than T state, interaction much less than kinetic energy state, where I see wave-like propagating behavior, a Fermi sea, a metal, versus the interaction much greater than T regime, where I see correlated state because the motion of one is inhibited by other electrons. That's the heart of correlations. You cannot consider the motion of one electron without considering what the rest of them are doing. And if you shift one, it tends to reorganize the whole system. It's correlation in that spirit, correlated motion. So interaction much larger than T, I will end up with a particle-like localized particle state called a Mott insulator. These two pictures, the left and right, are supposed to highlight these two scenarios. The left-hand side basically is filling up the density of states with up and down spin electrons, filling up the free electron density of states with up and down spin electrons. These are momentum states, eigenstates of the system, almost eigenstates of the system. They're filled up to the chemical potential, etc., etc. I get a Fermi sea. The right-hand side is a scenario where I should also not have left that single side vacant. I have particles essentially stuck to their reference sites without being able to move at all. Okay. If you write the wave function, it's a product over momentum states on the left-hand side. It's a product over position states on the right-hand side. They're not the same at all. Okay. In fact, there is no Fermi C, Fermi surface corresponding to the right-hand object. The Fermi distribution, the momentum distribution is completely flat, while the momentum distribution has a discontinuity of order 1 in the left-hand picture. A metal on the left, a localized cooperatively insulating state on the right. You would expect something non-trivial to happen when the interaction strength increases, and somewhere you will jump from the left picture to the right picture. This actually happens experimentally as well. It's not a theorist construct. This particular model may look overly simplistic, but it contains a germ of truth in that many of the oxides that one experiments on have this physics built into them. But how do you act? I mean, if you're a theorist, how do you access, quantify whatever is happening? So this is to frighten you with sort of the large number of states that entered the story and why a theorist's task is difficult. So in the absence of any obvious perturbing parameter, there are no small numbers. When you look at the interaction comparable to the kinetic scale, you say, okay, let me set up the Hamiltonian matrix, whatever comes out of it. So you just take a 4-side system in a ring geometry. 1, 2, 3, 4, sort of a closed geometry, periodic boundary conditions, and put 3 electrons. This is not even a molecule. Benzene has sort of 6 sides. This object has 4 sides, and you put 3 electrons in it, far from a solid. And then if you count the number of states over which the problem has to be solved, it turns out, next page, to be 24 basis states on which you have to diagonalize. And there is already a lack of intuition as to which of these 24 states are crucial in the story, which are subdominant, okay, in the absence of knowing U is big or T is big. U and T are comparable in this case. So 24 is tractable numerically, although you may not have enough analytic intuition as to what is happening. But a 4-side object is simply disappointing in terms of predicting any solid state properties. You may say, okay, so let us go to the next stage. I want to look at, and people who do theory know these sort of silly numbers on which sort of theorists compute their properties. Let me do a 16-side calculation using 4x4 geometry. You already have 100 million states involved in this. And if you wanted a solid within quotes of 100 sides, you have 10 to the power 55 states in it. So there has to be some intuition in the way you approach the problem. Brute force, I mean, going from 6 to 7, 7 to 8 sides is already multiplying computer time by factors of 10. So exact diagonalization is always a key reference calculation, but it's severely size limited. And to predict insulator metal transitions or change in spectral features or transport properties from this is a lost case right at the beginning. So what about perturbation theory? Well, the trouble with perturbation theory is perturbation theory invokes or assumes a continuity between the final state and the initial state. Okay. There is no change in symmetry. Metals don't become insulators under perturbation theory. Okay. So this adiabatic continuity constraint means that if you are a person looking at a Mott transition, perturbation theory is not going to yield an insulator for you. Whatever be the order of perturbation theory you do. And of course, very soon the perturbation theory itself becomes nasty and intractable. There is a recent tool from which some pictures I'll show later on called dynamical mean field theory, which has dominated the field of many body physics for the last 2 decades. Very powerful, conceptually pretty, but still has limitations. This, I mean, to use a phrase, is a theory defined in infinite dimensions. It basically means you're looking at a lattice with a very large coordination number where the theory becomes exact. Just as mean field theory for the Ising model becomes exact in infinite dimensions, the mean field theory, the dynamical mean field theory for electrons also becomes exact in infinite dimensions. Now, you could always say that I'm never in infinite dimensions, but qualitative physics can still be learned, extracted from that approach. But this quote-unquote large coordination infinite dimension constraint means that if you're a person interested in unusual geometries in 2 dimensions, this is not a very good starting point. So can we, in this very crowded field, make some difference? And that is where this classical, the so-called Langevin story, makes an entrance. So how do I bring in the classical to sort of, I've told you the limitations of an exact approach, exact numerics approach, perturbation theory being limited by its continuity principle. DMFT being very powerful, affording a way ahead, but there are spaces of limitation. What you do is start with what Mr. Hubbard and Stratonovich had defined in the 1960s, is to rewrite the problem. An interacting electron problem where electrons talk to electrons is hard because the states, you need to work with many body states. Okay. And the number of many body states explodes as the number of degrees of freedom increases. However, if you had a problem where there were non-interacting electrons in an unusual background to be determined self-consistently, exactly the way mean field theory works, you have a single electron problem. So the desperation is to somehow cast the interacting electron problem with its blowing up Hilbert space into a family of non-interacting problems in non-trivial background fields, background configurations. Is it at all possible? Well, the formalism here demonstrates it is possible with its own difficulties. So what you do is start with a trivial identity, which says that the Gaussian integral of over e power a x minus y square is root pi by a, trivial. Everyone knows this. Why am I writing this? This is to say that if you're a person who inverts this integral and wants to think of e power a y square, perversely, as an integral over a variable, well, e power a y square is integral dx times another exponential. The point is, I am not interested in e power a y square per se, but if I have the exponential of a quartic field, I can rewrite it as an integral over a new variable. So e power a 5 to the 4 is like the kind of interactions I'll get in my partition function from the Hubbard model or whatever else interacting fermion problems. The 5 to the 4 makes things intractable. I would love something which has quadratics in it. The way of rewriting the e power a 5,4 in terms of a quadratic in phi is to introduce a new variable. I call it eta in my integral, basically borrowing the principle, the Gaussian integral written on top, and say that at the cost of introducing a new field called eta, you can recast your interacting Fermi problem or interacting quantum problem in terms of those quantum variables moving in the background of a new field. The new field will bring its own difficulties into the problem. But at least formally, you have achieved something. This is a sleight of hand. I mean, sort of playing with algebra. Does it lead us somewhere useful in terms of making approximations? Now, partition functions involve integrals of powers of fields. To the extent those powers are quadratic, the partition function is doable exactly. The moment you go to quartics, you are lost. So, I mean, I've already said this. If you're looking at the lower part of my slide, then the Hubbard partition function was an integral over fermion fields, over Grassmann fields of exponential of some action. That action had quartic terms in the size, hard to solve. You introduce an object called a phi in the spirit of what you saw in the last slide. Lo and behold, you get an action which now looks, which only has quadratic terms in the size. But there is a phi psi bar psi object sitting there. Is phi psi bar psi an Isar object compared to psi bar psi square? Depends on how you approximate the phi sitting in this story. I may have lost part of my audience already, but I'll try to bring back the physics and depend less on the algebra somewhere down the line. So till now, and let me just look at my time quickly, we have spent about half an hour. What we have done is to move away from treating quantum mechanics or quantum many-body purely in terms of the original degrees of freedom, whose many-body states are far too many in number, and rewritten it in a quasi-integral language by introducing or recasting it in terms of those old fermions, the fermions you're interested in, coupled to a new space-time fluctuating field, which I call phi I tau. Phi I tau, phi r tau, whatever you wish it to be. Okay. So it's like saying that, oh, I had a Coulomb problem, electrons interacting directly with each other. I can rewrite the Coulomb problem by introducing a photon field. In fact, you often go the other way. You go from the electron-photon problem to the Coulomb But suppose you never knew of the photon to start with. Okay, the photon would emerge in some sense as a mediator between the electron degrees of freedom, and the interaction is now going to be between the electron and the photon and not between the electrons themselves directly. Now, that is the reality of electrodynamics. What you are doing is something, a bit of a fake. That is, does the field phi have a life of its own? Well, it has a usefulness. Okay. And what you learn from the phi theory will have implications for physical properties of the electrons. The question is, how do I know the phi configurations to use in my theory? Okay. And this is where something familiar comes in. If you said, let me treat the phi as a constant, space-time independent constant, a little thought would convince you that you just get mean field theory. The value of phi has to be determined consistently. Once you do that, you've ended up with a trivial garden variety MSc level mean field theory, where the electrons are moving in the background of a constant field or maybe a periodic field whose value has to be determined in terms of fermionic averages. That's the simplest approximation, not very exciting, and will give you poor phase diagrams. If you return the full time dependence of phi, but focus only on a single site, okay, you get what I sort of introduced as dynamical mean field theory. So there is the I variable, the site variable, and tau, the imaginary time variable. I and tau independence is mean field theory. Tau dependent but I independent is what we call dynamical single site theory, dynamical mean field theory. For those brave enough, if you written the full I and tau dependence, you end up with what is called the quantum Monte Carlo problem. You sample over space-time fluctuating configurations of the phi, get your family of optimal configurations, and solve the fermion problems in those backgrounds. Numerically exact and very hard to implement. There is, this arrangement will tell you, one last possibility where you ignore time dependence, the tau dependence to start with, which is where classical enters the story, but look only at spatial fluctuations. I mean, you'll remember from classical statistical mechanics that you look at spatial fluctuations of the field, the time variable is not important in the classical problems. So here, if I drop the tau dependence but retain the full spatial variation in the problem, I end up with what is called a static path approximation, SPA. You don't have to worry about the name. So it simply means that I'm not looking at the time aspect of the problem. Electrons are moving in spatially fluctuating configurations, but those configurations don't vary in time. There are a family of spatial configurations over which the electron problem have to be solved, averaged over to get to physical properties. But I don't need to look at the dynamics of those configurations when considering the electron motion. Now, static spatial configurations are like free electron problems. I mean, they are non-trivial free electron problems because the configuration is not periodic. They could look very complicated, but nevertheless, once you have electrons in a potential, the eigenstates are stated determinants. Okay. So I have, if you do this, and if it has some content and strength to it, then what will happen is you can end up with an approximation of electrons coupled to classical backgrounds. I have to speed up a little bit. Well, we have come near the end. Let me see what we can do with this kind of an approach to the Mott insulator problem. Very quickly on this Mott insulator, band theory predicts that a half-filled band should be a metal. Well, half-filled is because you've filled up states from the bottom of the band to its center. The Fermi energy is at a point where the density of states is large. N of EF is finite, so I should get a nice metal. It turns out that when electron interactions are present, that band actually splits. My Fermi level lies in a gap. I get an insulator. And there are experimental realizations of this going back to Mott's time in the 1920s, starting with nickel oxide. This is a picture of vanadium oxide. And hundreds of such materials have been discovered, which are predicted to be metal from density functional / band theory, turn out to be strong insulators because of the presence of correlations. And you can actually tune across this transition. Some of these materials are close to the metal insulator transition, and by applying pressure or by sort of exerting chemical pressure or physical pressure, you can go from one phase to the other. And there has been no convincing theory till the 90s. This slide is to show that these DMFT people, I mentioned DMFT as an approximation where you think of single site oblique large dimensional approximations retaining the quantum fluctuations at a site but ignoring the spatial variation across the lattice. These people came up with a successful scheme, which actually, if you look at the pictures here, the top left picture is one with a sharp central peak in the density of states. It's a metal. The bottom right shows that the peak has vanished and ended up with a gap. So this is a 5-second demonstration of going from a metallic state to an insulator as you increase the interaction strength. U across a critical value, UC. So there are existing theories of the metal insulator transition. I cannot take credit today by saying, oh, we are the first to have solved this using this classical whatever business. No. I mean, more than 20 years back, people have done this. But there are limitations to the approach, and it's always worthwhile to see if a second way of looking at the problem leads to some insight. So what does the classical fluctuation approach do in these kind of situations? More lines of algebra through which I'll just sort of cut through to say that when you look at the parent many-body problem of interacting electrons, you introduce fields to decouple it. I don't want to look at interacting electrons directly. I want to look at electrons interacting with background fields, which are two in number. One is a scalar field called phi, another is a vector field called M, a magnetic field called M. And ignore the top part. If you retain the spatial fluctuations, you end up with an effective model, which is the fermion, the parent electron coupled to a field called phi, it's a charge field, and a vector field called M, which is a local magnetic field. It's a local Zeeman field. Now, this is, within quotes, a free electron problem. Free in the sense there are no electron-electron interaction terms. All that you have is an electron coupling to the M and an electron coupling to the phi. If the M's and phi's were given, you can solve it in 5 minutes. The M's and phi's are not given. So the difficulty of this approach is that while you reduce the electronic problem and its physical property calculations to essentially a family of free electron Hamiltonians, you don't know the appropriate configurations for the background fields over which to average. So who tells you how to pick the M and how to pick the phi? So this is where the story comes to a close. So the electron problem, I have dropped the phi because of its irrelevance. The electron problem basically is kinetic energy in the lattice and the sigma, the spin of the electron coupled to this local vector field called M. But who tells me how to pick the M? The M's are governed by a Hamiltonian, which is this nasty object called the log trace of the fermionic problem and some stiffness term. Now, this can be frightening to someone, and it needs a little bit of time to digest what is going on here. So I can arrive at the distribution functions for the M's by eliminating the electrons from the problem, the tracing over the electrons in the problem. Sadly, the trace cannot be performed analytically. So this is where numerics enters the story. So the twofold the two steps in the problem are solve a family, not just one, but a family of electronic problems in background configurations called M. Pick the M's from a Monte Carlo strategy defined by the Hamiltonian HMI given here. If HMI were a Heisenberg model, you would know how to generate its configurations using Monte Carlo. If HMI were a Ising model, you would do the same. HMI is a more implicit object here because the weight for the configuration depends on the electronic free energy. But the upshot of all this is between equation 1 and equation 2, I have rewritten the parent many-body problem of interacting electrons in terms of electrons moving in a family of classical background configurations. And the strategy adopted here is basically one of sampling those configurations and solving the electron problem in those backgrounds. It's many, many free electron problems in backgrounds which are very non-trivial and generated by an annealing procedure. But computationally, it's much cheaper than doing the full-blooded sort of many-body diagonalization. Let me skip this part and come to the Rajva part, because I think we should close in time for bottom stock. So the last slide showed that there is a strategy where you can reduce your parent many-body problem, where I was looking at the Hubbard model. You can look at superconductors, you can look at Fermi superfluids, magnets, and what have you. All of them are susceptible to this kind of a treatment. So you can recast them in terms of fermions coupling to classical background fields, anneal those background fields, go back and diagonalize the fermion problem over those family of configurations. But this is what I call a sampling strategy. Okay. In the spirit of what I mentioned right at the beginning of the talk, this will give you the partition function. It will not give you the dynamics of the problem. So just as standard statistical mechanics had a sampling or tracing approach to it, and an equivalent dynamical approach via the Langevin, there is a corresponding Langevin equation I could have written for the magnetic degrees of freedom. So instead of sampling them, I could have just evolved them in time. And the corresponding Langevin equation, remember what I wrote way back in the first slide, is the dmi dt is related to a torque term, which is the equivalent of a force term you saw earlier, a friction, and a noise. Okay. And the correlation functions of the noise follow the standard fluctuation dissipation rule. Now, so this is an equation for him. What happened to the electrons? Well, the electrons are hidden within what I call the HSF, the spin fermion Hamiltonian. So HSF is a non-trivial object. Calculating its derivatives with respect to Mi is a complicated but essentially a one-body operation. It's not a many-body operation. And if you can calculate those derivatives, then you can time evolve the M field on your lattice and end up with whatever you want at the end of it. So my last but one slide is to say, there are parallels and differences with the original Langevin equation. Both the garden variety Langevin equation as written down by Langevin and the equation I showed you here involve a force derived from a Hamiltonian, a force or a torque derived from a conservative Hamiltonian, a friction or a dissipation term, and finally a noise. So force or torque, friction, noise. The commonality in the structure. Both of them lead to long-time distributions, which are essentially Boltzmann, which is why Monte Carlo matches with whatever dynamics gives you. But the original case was for a single particle in a thermal bath. What we are doing now is evolving a field. M of RT is a field for which you've written a Langevin equation. It's a partial differential equation in the presence of a noise. So technically, it's more complicated. The forces encode the classical quantum difference. Del V del R is a very explicit classical force derived from a potential V of R. Now, del H del M, as sits on the right-hand side of this equation, actually encodes the quantum nature of the problem. And now this, okay, here. Because the H average includes the fermionic free energy. So all the physics of electron delocalization and its interactions with the magnetic field, etc., the magnetic moment, are hidden in this compact object called del H del M. So the quantum mechanics of this problem is not so much in some Hilbert space structure, but in the way you compute forces as derivatives of a spin fermion Hamiltonian with respect to the field called Mi. Finally, the original scheme described just a single particle in a thermal bath, essentially diffusion. This new scheme, where you're looking at the evolution of a field configuration, can describe magnetic order, superconductivity, Mott transition, you name it. All the solid-state phenomena that you were interested in earlier have now a version available in terms of a semi-classical dynamical equation. So we conclude now. The quantum many-body problems are at the heart of correlated matter. It goes without saying. The difficulty lies with the exponential growth in the number of states involved, and our ignorance of which of these are relevant. I mean, there are ways to make some headway, but we really don't know in most problems how to truncate the Hilbert space to the relevant number of states. What I demonstrated was that under some circumstances, it is useful to recast this fully interacting problems as a quantum particle in a classical background. These are computationally more tractable than the full quantum Monte Carlo and allows access to both the thermal physics and the dynamics, if you were a dynamics person. And if you say, but some quantum mechanics has been lost, indeed. If you go to low enough temperatures, some quantum mechanics is lost, but this can be the starting point of a fuller theory which builds back the quantum fluctuations. So it's a beginning in a certain direction. So with that, and having taken a little more than my allotted time, thank you. And back to you, Ajit.
Thank you, Professor Majumdar. Beautiful talk. Very, very nice talk. Okay, it's open for discussions now. So whoever wants to ask questions, please unmute yourself and ask questions.
Okay. Ajit, can I ask the
yeah, please go ahead.
Can I ask the question?
Is it Devkant or Ajit? Who is it?
Yeah, I can ask maybe after Ajit asks.
Okay, Ajit, you ask first.
Yeah, hi, Pinaki, Ajit here.
Yeah,
please.
Yeah, so with your approach, I mean, so probably you have investigated, do you get the Mott phase correctly?
No, I skipped all of that. Yes. We did. In fact, this goes back to Rajashi's work. So there are standard things. The Mott insulator has been investigated on square, triangle. So we did model problems, and with Nyabanta we did real materials like pyrochlores. So this has been done and dusted. Okay. So, and look, the point is, there are situations where the old dynamical mean field theory works very well, but if you look at frustrated geometries, where the spatial character is very important in the Kagome lattice, in the pyrochlore lattice, then this kind of a method which respects the spatial character has an advantage. But in the older cases, DMFT has answered most of the questions. So yes, we do get the Mott phase also.
Okay. And second question is related to like, if I, so your method, if I want to use with some Hamiltonian with spin orbit coupling, let's say, like the Ken-Meillet, Hubbard.
Well, absolutely. The spin orbit coupling will go into the sort of single body part of the Hamiltonian, isn't it?
Yeah, right.
So the single body part is being treated exactly. So to the extent there is spin orbit coupling or topological features in the band structure, they will all be written exactly in what I call edge kinetic, the quadratic part of the Hamiltonian. So the approximate treatment comes only in the U, okay, the quantum fluctuations associated with the interaction itself. The band structure details of band structure or whatever one body part we want to put in is essentially exactly included. In fact, in the iridates, I mean, to just give you an example, the iridates are famous examples involving spin orbit coupling. And part of Nyabanta's thesis had to do with understanding the correlation effects in the iridates in addition to the role of spin orbit coupling. So we did also that.
Okay.
All right. I have Professor Pinaki, nice talk.
Yes.
So I have some three questions from an experimental perspective. Some of my doubt clarification.
Please.
So why? Because we know most of the oxides, whether it is 3D transition metal or you talked about iridates, they most show the Mott physics or the Hubbard formalism. So my question is, and generally what we understand, this 3D, the spatial constant, the orbital spatial constant is limited. So the Coulomb U, we get little more. So that's what typical textbooks and other people write. But the question is, if I have the same ion or same atom 3D in some alloys or different kind of materials, but there we don't see much this kind of physics.
Yeah, but it's okay. So let me answer the first question to start with. I think it has to do with the ligand. The fact that there is the hopping in the oxides takes place through oxygen. So it is not just the size of the copper orbital, but the copper hopping, which is what ultimately gives you the bandwidth. This object is limited. So if you look at copper itself as a 3D element, copper is a large bandwidth. It's a very good metal. Once you go to the copper oxides, the presence of a bridging oxygen reduces the effective hopping, and this suppression of the kinetic energy enhances the relative value of interactions in the problem. So the bandwidth is not just controlled by the nature of the D element, it also has to do with how one D electron jumps to the next D site. So it will very much depend on what your compound involves in terms of the bridging element or ligand. In the oxides, it turns out the oxygen P orbitals leads to a suppression of the hopping. In the situations you're talking about, it is quite possible that the effective bands are still broad, and I don't end up with the kind of kinetic suppression that you see in the oxides.
Yeah, but the point is, I mean, that the bridging element can be, because nowadays people are a lot working on these chalcogenides and other things.
Yeah.
They are also the bridging element chalcogenide, but the physics, like the fascinating physics of oxides, that's not very much reflected there. Those are some.
Yeah. So the question is what I mean. So okay. So this question really ought to be answered by a band theorist. So people who do DFT calculations can tell you what are the relative values of a crudely estimated Coulomb U and the bandwidth if you look at the chalcogenides versus the cuprates. Okay. In the cuprates, one believes that the value of U by T is of the order of maybe 4 to 5. In the chalcogenides, is it more in the range of 1 and 2, or is it 4 and 5? That will dictate whether you're in the strong coupling regime or somewhere at relatively weaker values of coupling. I don't have an answer offhand about these numbers.
Okay, fine. So that is another thing, because now there is a buzzword in the community. They talk about quantum materials.
Okay.
Where the correlated electron system is a part of it.
Okay.
And there are many topological, they call it Dirac material, while. And how they define, that's what just I wanted to know, because you will be the right person to clarify. They define the quantum material is that material where the quantum effects manifest over a wider range of energy and length scale.
Okay, fine.
So that part I am not able to wider, because I know quantum effects is much more when you reduce the dimension.
Yes.
But they are telling quantum effects manifest over a wider range of energy and length scales.
Well, energy one can understand. The point is, if your quantum effects are very fragile, let us say. So if you look at liquid helium, to give you a sort of offbeat example, you will see helium liquids behaving as quantum liquids only at a few Kelvin. If you look at helium, I mean, of course, helium will vaporize. At higher temperatures, the quantum effects are gone. It's essentially a classical liquid. If you look at a heavy fermion, for example, in a heavy fermion material, quantum effects show up on the scale of 10 Kelvin. By the time you're at 50 Kelvin, it's essentially a classic. So you want the quantum phenomena to survive on energy and temperature scales which are accessible at room temperature. For instance, if you look at the quantum Hall effect, no one measures quantum Hall plateaus at 300 Kelvin. To see those effects, you need to go to millikelvin temperatures. And I think the push would be towards having this phenomena show up at more accessible temperatures and energy scales, not at microelectron volts or millikelvin temp. The spatial scale argument, I'm not very sure of what it actually means. You're right that quantum confinement enhances a certain kind of quantum effects. I'm not sure what they exactly mean by saying that increased spatial.
Yeah, that part I could not. This is a review
I
by this day.
have a simple understanding of that particular usage.
Okay, all right. This is my last question.
Yeah.
So we are very much familiar with metals like coppers, and we know this is just a free electron, not correlated system. And we know that in a correlated system, as you mentioned, they cannot be described by this Bayer-Coulomb interaction between a charge and the background. So now the point I'm asking in a different way, if I want to design a correlated electron system, I know what are the signature of a correlated electron system, as you told, they behave in nonlinear fashion in those kind of complex way. But if I want to design a correlated electron system as an experimentalist, what should I look for?
Yeah, I thought you sort of, your first question has some answer to that, in the sense, I mean, firstly, the material has to form. In fact, there is an entire industry, I believe, today of first principles people who try to sort of computationally design materials with certain properties. Now, the trouble is all combinations of ABC do not form stable materials. What I would look for is an object where correlation basically requires that the relevant interaction scales are larger than the bandwidths in the problem. So you have to have orbitals and hoppings between them, which are small compared to the native Coulomb scale on those orbitals. Now you can say, okay, start with, let's say, ternary compounds, where the central D or F electron site is bridged by some object. The difficulty, of course, is you don't know whether when you try to synthesize that object, it's actually going to form. So computationally, it's possible to make various statements about taking A2, B4, C6 kind of materials. In fact, in the double perovskites, a lot has been done. The difficulty would be in actually knowing the synthesis conditions under which this material forms a single phase object. So my computational colleagues have come up with many predictions where you could get a correlated material, but I think only a handful of them have been achieved.
Mm-hmm.
People don't know what kinetic pathways to take to actually build that material together into a single phase object.
Okay, thank you very much.
Yeah.
Nice.
Actually, now since the time is, I being the conducting the session, I think I also have some right to ask question. Can I ask?
Yeah, go ahead.
Okay, just a very quick question I'll ask because of the time. So your proposal actually in the spirit of Hubble-Skatanovich transformation.
Yeah.
You are transformed. So basically, you trade off the original things in terms of the background field, phi and m.
Right.
But I wanted to ask you. So your main proposal is that for the evolution of the field m, you are proposing a Langevin equation, which is a Langevin equation for the field. That's the main ingredient.
Yes.
Now, as I expect, I mean, because it's a Langevin equation for field, in large time limit, you should expect to get a thermal equilibrium distribution for the field. Isn't it right?
Right. Right.
So will that be the limit?
Yeah.
For
Yeah. So Ajit, I mean, there are answers at various levels. So firstly, I put the Langevin equation out of a hat. Okay.
Yeah, I know. That's one thing.
What you really do is write what is called a Keldysh path integral.
Yeah.
And from the Keldysh, you can write down a kinetic equation. That kinetic equation under various sort of push and pull reduces to a large. So why did I write a gamma kt on the right hand? So the noise that you should really use in the quantum case is not thermal noise, because the thermal noise will die off as temperature goes to zero. So the noise that should truly describe the quantum systems I'm talking about is a far more non-trivial object, which is correlated in time, has a colored character, etc., etc. So what I wrote down was, if you wish, a garden variety of that, which by its construction will satisfy the Boltzmann distribution.
Okay.
Because I have chosen my noise strength to match with the dissipation coefficient. The left and right sides have been matched. And you indeed discovered that the distribution function you get from the dynamics matches with configurations you get out of the Monte Carlo. But this is sort of a bit of a concoction. Ideally, this equation should have been derived from a more first principles approach, which we have done. I mean, there are elaborate sort of 6-page derivations in various places, but the true equation that you end up using this strategy is far more complicated than the simple looking Langevin equation I showed you. So for tractability, I use the simplest form, and we will use it as a starting point to build in some of the physics which you talked about, which may or may not at long times lead to the kind of state you're talking about. For instance,
sure, I understand.
Yeah. So I just think of it as a first step in the direction. There is a lot more that needs to be done to establish a conclusive theory.
Okay, thank you very much. Yeah. I think we should, under the pressing question, we will close the session. Is there a really pressing question by somebody? Okay, no. Well, thank Professor Majumdar for a beautiful talk and very nice discussion.
Thank you.
Thank you.
Right.
Professor Gautam Bhattacharya, welcome. Okay, Professor Som, who will coordinate the next session?
This is Professor Agarwal.
Okay. So I'll close my thing. Professor Bhattacharya, good afternoon. Yes, sir.
Okay, so our next speaker is Professor Gautam Bhattacharya, the Director, Saha Institute of Nuclear Physics, Kolkata. On behalf of the Director IOP and larger IOP community, I welcome him to IOP Foundation Day technical session. It is my pleasure to introduce him. Actually, Professor Bhattacharya has been primarily working in the area of particle physics phenomenology. His main interest has been to explore new scenarios that go beyond the standard model of the particle physics. In particular, he has been interested in dynamics of electroweak symmetry breaking, supersymmetry, extra dimensions, composite Higgs, dark matter, etc. Actually, his work and review articles on R parity violating supersymmetric models are widely known. For his academic achievements, he has received many awards. He is a fellow of all three major Indian academies, INSA, NASI, and Indian Academy of Sciences, Bangalore. He is also a JC Booth fellow. He has been also exploring, actually, in his academic activities, various electroweak symmetry breaking scenarios. Okay, and today he is going to tell us about history of one such scenario. So that scenario involves discovery of a scalar particle known as Higgs boson in 2012 at LSC. So title of his talk is A Brief History of the Higgs boson. So now I would request Professor Bhattacharya to deliver his talk.
Can you hear me?
Yes, we can hear you.
Okay. So it's a great honor for me, in the first place, to be invited as a speaker in the Foundation Day of IOP. Now, before I start my lecture, let me express my the connection between SINP and IOP. I mean, probably all of you know that when IOP was founded, Professor Pradhan was in SINP at that time. Although I was not there at that time, I was a friend of, a good friend of one of our, one of the secretaries in the theory division, who has expired some years ago. And he was a young secretary of the TNP division, it's Theoretical Nuclear Physics Division, as it used to be called in that time, the theory division. And he was, again, of the same age group as some of the PhD students of Professor Pradhan. One of them was Avinash Khare. Now, Jayanta Babu, I mean, the way we knew him, the secretary used to tell me how he and Avinash used to take many trips to Bhubaneswar to help Professor Pradhan, when he was doing the twin job, I mean, like teaching and doing research in SINP, and at the same time taking a lot of pain in, in the initial phase of founding IOP, Institute of Physics in Bhubaneswar. Now, well, I mean, both the senior professors of IOP I knew, Professor Avinash Khare and Gyan Moharana, also, sort of told me many stories about the early days of IOP, although I didn't have the opportunity to visit IOP many times, but only a few times in different capacities. Once as a PhD student of Calcutta University, there was some small meeting in Tosali. There was a conference in Tosali Sand, and we made a short visit to IOP at that time. And then in recently, for some other reasons, I visited IOP. But I have been a good friend of many of my colleagues in IOP, Professor Khare, Professor Maharana, and then later on, one of your previous directors, Sudhakar Panda, is known to me for a long time. One of your council members, Surjo Nayak, and me were doing PhD in different places. He was in IOP and I was in Calcutta University. We were in touch. I mean, I have been in good contact with IOP and also Ajit. Ajit Srivastav. I know him since I don't remember since how many years. Many years. I don't know whether Ajit remembers that. And many of us are well, connected to each other.
Of course, I remember.
Yes, okay. So IOP is not a new place to me, and I'm really privileged and honored to be asked by the director of IOP to be one of the speakers on this occasion. Now, today I will, it is going to be the kind of talk that I'm not used to giving. I'm more comfortable giving technical talks on my own work. But today I take the opportunity of, it will be like storytelling. Some of the stories about, some of the lores or whatever facts or myths about the actors behind the discovery, which I heard and sometimes overheard in the corridor discussion in many different places, and sometimes in the picnics, in theory division picnic at CERN, where many people who were involved, like Brent Key, who was once the leader of theory division, was already retired when I was there as a postdoc, and subsequently spent some time in my sabbatical. So Prentke used to join us, and also Jack Steinberger was a regular, visitor to the theory division, both during the colloquium and seminars, as well as during the picnics, when he used to tell us his experience. So my experience, or whatever as I said, I heard and sometimes overheard from other discussions about the different things that went behind this discovery, and some of the things I read from some books, which are basically a collections of reminiscences of by various authors who happen to be also high energy physicists. So let me straight away now go to the talk. Let me share my slide. Let me see how I do that. Yes, I think, yes. Yes, stop. No, it's okay. No, is it a full slide? I don't know. Is it a full screen?
Yes, it looks like.
It looks like full screen. Can I? How? Let me see.
It's not a full slide as yet.
It's not.
Maybe you can broaden it a bit.
But it looks okay.
It can be just a bit. I think this is your XPDF, whatever you are using.
PDF.
Yeah, so you can just enlarge your just file within the within the application.
Just 1 second. Let me see whether the other things work. Then it is okay. If you are comfortable with it, I want to play around and mess it up. So is it okay?
Gautamda, you can do full screen.
Yeah, that's what. So it is let me
you
see.
Go to view.
Yes, and I can see full screen. Yes. Full screen. It is full screen now.
Yes.
Yeah. It's now better. Yeah.
It's now better. Okay. So, well, the first slide doesn't need any more view. So I go to the second slide. So let me start, from it's like storytelling. Something I sort of assembled from different sources, primarily one of the books on popular, particle physics in the present context, in the context of Higgs discovery. And as I told you, from whatever I heard and overheard from many different people. So, and this is some of the very basic things. You will not hear anything new in my talk, for sure. So, well, the title of the slide is very clear to you, how to tame the infinity that we encounter in quantum field theory. Now, historically, if you go back, say maybe 100 years from now, or more than 100 years, 120 years or so, the situation was that Maxwell's electromagnetism, which described light as electromagnetic waves, then Einstein's special relativity, well, everybody knows about E equal to mc square, and quantum mechanics, which explained the stability of the atoms and the beautiful spectral lines, the Balmer line, the Bastian lines, all the hydrogen spectra, for example. That worked too well. Now, quantum electrodynamics, which was created from the union of these concepts, namely electromagnetism, relativity, and quantum mechanics, to describe how light interacts with matters, with atoms, faced an ugly roadblock, and that's the infinity. Essentially, vacuum is not empty. Now, it is full of particle and antiparticle pairs bubbling with, these are the transient particle-antiparticle pair. And the electron interacts with its electromagnetic field. Now, quantum mechanics tells you, the uncertainty principle, that for a very split second, or for a very short time, you don't have to conserve energy and momentum. So a particle can, decay into other particles, which then, recombine to give back the same particle. Now, during that mayfly, I mean, during that, momentary, period, I mean, the short period, the field also changes, and that contributes to many things like the self-energy of the particle. Okay. Now, when people try to calculate the mass of the electron and the charge of the electron, all these effects means the effect of this transient particle and antiparticle pair that bubbled up and sort of changed the electromagnetic field of the original particle, namely the electron. For example, electron can emit a photon, it reabsorbs the photons. So what happens if you take into account all these things, all the intermediate virtual particles, all the possibilities, you have to add up, and that give rise to an unacceptably large number, which is infinity. Now, in that case, what happens? I mean, although you might expect that if you go to higher and higher orders, things will be, you expect to get smaller numbers. You get something like 1 plus half. If it is 1 plus half plus 1 by 4 plus 1 by 8, then the sum is 2. But instead you get like, I mean, it's not exactly like that, but even though the subsequent numbers are smaller than the previous number, like 1 plus half plus 1/3 plus 1 by 4, the sum goes to infinity. So that was not what was expected, and that's the ugly roadblock I'm talking about. Now, at that time, I mean, the way we are, we sort of recall our history, the situation was such that many bright people left physics at that time because they thought this is an unsurmountable kind of roadblock which cannot be, I mean, it's better to look for some other career. So people left, bright people who could have done, wonders, left physics or moved to some other branches. Now, Willis Lamb, around that time in the 1930s, he measured a split in the electron energy levels in hydrogen atom. I mean, two levels should have identical energy according to Dirac equation. So what he measured is a 1 part in a million difference in energy, which should not have been there according to Dirac equation, which says no splitting. Now, he came to Shelter Island Conference in early 1930s. I don't remember the year. And, he reported the result. Pauli was in Zurich at that time. Of course, he was always in Zurich. And he had a very bright, young, I shouldn't say postdoc, but maybe a junior research colleague, James Robert Oppenheimer. So Pauli asked Oppenheimer to do the calculation, and not according to Dirac equation, but with the help of QED. And of course, the result was infinity. Well, I mean, it was such a pathetic situation that it required some genius to step in and eventually sort out the problem. Now, I'll not get into the details of this historical development, but ultimately, people found that when they try to calculate, for example, the mass of the electron, okay? Now, mass of the electron is like calculating, you have to first calculate the self-energy. I mean, what is that? I mean, it is like a snake eating its own tail. I mean, from the same electromagnetic field, it is gaining its energy. You try to calculate the self-energy of the electron from its own electromagnetic field. And since energy and mass are equivalent, you will find that you encounter this infinity, that the energy and mass shot up to infinity. However, And the same thing happens for the electric charge. But of course, it's a nonsense result because you can measure the mass of the electron, and that is what ultimately matters. Now, it was observed by by people. I mean, these stalwarts eventually. Like, for example, Schwinger did the calculation, followed up by Feynman and many other people. But these are the leaders. That the infinity that you when you try to calculate the Lamb shift, the infinity that you encounter is the same expression, is the same infinity that you encounter if you try to calculate the self energy, which means by some practical means, if you can calculate the mass and the electric charge and use those measured values in the Lamb shift, or in, for example, the tiny magnetic moment, it's called the anomalous magnetic moment of the electron, you get a finite result. It means don't do the entire calculation from the first principle. You'll encounter something which is infinity, which is a nonsense result, and that has to do because of the limitation of your technique. Instead, you use the measured values and replace the measured values in the calculation of the Lamb shift or in the magnetic moment of the electron. And you could do that because the nature of the expression of the infinities are the same in all these cases. That also has a profound implication. Now, this technique of using known values to calculate other values eventually became known as renormalization. Now, what is this QED? It's a gauge theory. Gauge means phase, okay? Where at each point in the space-time, the transformation, you have an intrinsic degree of freedom which you did not specify. I mean, for example, there is you can change the phase of the particles involved. For example, an electron, and if you have to maintain an invariance, you have to do it at each, and you want to have this, a different amount of rotation or the phase transformation at different points. You need to do that both for the electron, and of course you need the photon, right? So it's kind of an automatic choice for you, and which will naturally come in as the carrier of the electromagnetic force. So that is QED. Now, gauge invariance implied that regardless of the accountancy of your computational scheme, I mean, it doesn't matter which way you do your computation, okay, you get the same result, and that is the invariance. Now, it is, of course, as I mentioned, that it is a profound scheme that ensures that photon is strictly massless. Means the carrier of the electromagnetic force is massless, the photon, and that is, well, but even at that time it was experimentally known to be correct. I mean, photon should not be massive. Eventually, gauge theory involving more than one fermion, not just the electron, but for example, a pair of fermions like a neutron and proton, I mean, was constructed. So QED in that case, it's more than just a QED involving one electron and one photon, but QED involved, I mean, it's like a QED, but for the, a little bit advanced. So since it's two element fermionic set, the algebra involved matrices. What happened? Naturally emerged are electrically charged massless photon-like objects. I mean, this is something that we were not prepared with. We didn't have that kind of evidence from nature, and that was contrary to what was experimentally, I mean, there was no experimental support for that from many different aspects. So this was an impossible situation. Well, I don't have to go through the detailed development of the weak interaction, but this was eventually giving way to explaining how weak interaction would be constructed. And by then, the role of weak interaction means the weak nuclear forces, both for radioactivity and for burning the solar fuel. I mean, you need 4 protons to be clumped together by strong interaction. And eventually the role of the weak interaction is to give you the helium and the photon, which, the photon sort of bounces back and forth within the within the sun. It takes 100,000 years within the suns, but eventually it comes to the surface of the sun. It takes 8 minutes to reach you. But only because of the weak interaction, you get the sunlight. And also radioactivity was another thing, that is an evidence. So the evidence of weak interaction was manifest in both these processes. Now, so what is the carrier of weak interaction? You need, of course, more than something what was already known. Photon was the only known carrier of the gauge force. And as I told you, if you involve more than one fermion, for example, neutron and proton, just as an example, you automatically naturally get more than one gauge bosons. So here also you need more than one gauge boson. Not only a gauge boson, it has to be electrically charged gauge boson. And of course, with neutron and proton, if you try to construct a QED-like theory, a gauge theory, you get a charged gauge boson anyway. But because the weak interaction is short-ranged, you expect that gauge boson to be massive. Okay, but the gauge invariance told you that photon is strictly massless. So another problem. And here experiment tells you that you need not only a charged gauge boson, it is not a massless gauge boson. In the meantime, in the late 50s, in 57, there was this weak interaction was found to be of V minus A nature. Okay, and there was a speculation eventually that the electromagnetic and weak interaction may have a common connection. But the burning question was how to reconcile the gauge invariance, which essentially required the masslessness of the photon with the necessity of a massive gauge boson. Because if you have the massive gauge boson, then the infinities, which was tamed, because of, in the QED, infinities was tamed, I told you. And the masslessness of the photon played an important role. The gauge invariance played an important role. So the infinities would come back. So by trying to solve one problem, you shouldn't get back the problem that you already solved. Then something was also, cooking up parallelly, which is the role of symmetry in physics. The idea came, people not only engaged in high energy physics. Well, at that time, what was high energy? It was medium range energy in today's term. But those, who were sort of moving from the traditional nuclear physics to subnuclear domain was also looking at something that the newly emerging condensed matter people, what we today call the condensed matter people, this bifurcation was happening around that time. Now, all of them were looking at the role of symmetry in various contexts. Now, apparently this slide may look to you as something, because you know the thing, you know the connection, but those of you who are not, maybe the students or in other areas, it may look somewhat not connected to the theme that I was talking about, but you will eventually see that they're intimately, inextricably connected. Think of this banquet. It's called Salam's banquet. Maybe Salam gave this example. It's a round dinner table, but wherever you sit, you have a glass on your right and on your left. Now there's a perfect symmetry. Okay, so you could choose something on the left, something on the right, but the moment you choose, any of you chooses the one on the right, everybody else will have to choose the one on the right. So the symmetry is broken. Okay. Now I will eventually, tell you that the symmetry is not broken; it is hidden. But okay, I mean, so the solution of it's a perfectly symmetric world, but for something that might have triggered for some reasons which I don't want to know. For example, I don't want to ask you why did you choose the one on the right and not on the left. But the moment you chose the one on the right, everybody else will have to choose the one on the right, and the symmetry is broken. Think about water molecules. It is a perfectly rotational symmetry when, it can go in any possible direction, 360 degree, okay? But the moment it becomes ice, okay, so depend in a sub-zero temperature, for example, the snowflake has a rotational symmetry, which is like 60 degree rotation will bring you back, to the identical condition. Okay, so it becomes like a discrete symmetry. So the symmetry of these water molecules in the sub-zero snowflakes are less than the symmetry it enjoyed when it was like in 10 degree or 20 degree situation. So the rotational symmetry that was there in the original situation is somehow hidden in a different phase, which is the in the sub-zero temperature in the snowflakes. So somehow transition from one phase to another hides the full symmetry, and you go to a phase having lesser symmetry. The same thing, similar thing happens in the context of ferromagnetism, which I didn't write in this slide. That, for example, below a certain temperature and above a certain temperature, the orientation of the tiny magnets. In one case, it is perfectly, symmetric. It can point to any direction above a certain temperature, but below a certain temperature, it is aligned in a particular direction. Similarly, in the context of superconductivity, the same thing happens. Okay, that the symmetry that gets hidden is essentially the gauge invariance of electromagnetism. Okay, and it happens due to organized Cooper pair bonding. In a very simple way, you think of it. Let me give you a very crude example. Like if you pass through a tunnel, for example. Suppose you are driving, you are going through a tunnel. You will see that your mobile reception is pretty bad. Okay. But if you have a compass, it will still point to the north direction, which means the magnetic field is not hindered, but the electromagnetic field, which the exact, okay, so that you need to be fully functional in order for your mobile to be fully operative is not there. Now, in a conductor, you will see only on the surface the electric field is there. Okay. Similarly, in a superconductor, inside there is no magnetic field. That is the Meissner effect. Magnetic fields are repelled. So the bottom line is that, if the electromagnetic field is not uniformly distributed everywhere, then you might think that it is not infinitely ranged, which means that if it is inside the superconductor, because of the Meissner effect, the magnetic fields are repelled, and only on the surface it is there, then you might feel as if the electromagnetic field is short-ranged, means it is not penetrating everywhere. Which has the implication that if it is short range, then the corresponding gauge boson is massive. So inside what was known as, I mean, it was a very crude kind of analogy, but inside the plasma that Anderson thought about, it's a non-relativistic plasma. The photons seem to have mass. In fact, which means that the original electromagnetism, which relies on masslessness of the photon to ensure gauge invariance, suddenly created a situation where photon became massive. So the symmetry is lost. So it is not that the gauge symmetry is never broken. The global symmetry, which is gauged, okay, the generator which generates the global symmetry, maybe in some direction it is broken, and if the gauge field along that direction might seem to become massive. So this is the technical, in a technical way, this is how it is said. But whenever you have a global symmetry and that is spontaneously broken, you have a situation which will somehow be linked. Now, I'm going to tell you to the problem I was mentioning in my previous slide, namely how to encounter the massive gauge boson that, sort of brought back the bad memories of infinity. Now, so there are two situations. One is that you have suppose you have a spontaneous symmetry, so a continuous symmetry, it's a global symmetry, and that is spontaneously broken. What you get is a set of massless bosons. Now, this is again a disastrous situation. In nature, there is no such massless scalar boson. Okay, this is a problem. Now, the point is, this is the second problem. The first problem, well, it is not that, how do you know this is the second problem? This is another thing. There was already a problem in the literature, that is, you have to encounter the massive gauge boson, which brought back the bad memories of the infinities. And now you encounter another problem, which is a set of massless gauge bosons, massless scalar bosons, which are again contrary to what nature allows you. Now, whether it's a problem or an opportunity, sometimes if you have two problems, some genius can see I mean, in a general sense, I wrote it, I mean, as if there are n such thing, but think of one such thing and assume that you have one photon which is massive. Now, one massive photon, it may be a charged photon, massive, already gave you a problem, and you are trying to, marry it, marry that problem with the problem of a massless Goldstone boson, and can you go to a situation where there is no problem? So that was the entire goal of the physicists in the late 50s, early 60s, and primarily from the 1958 onwards, 1958-59 onwards, and the problem got solved. It took about 5 to 6 years. And there were efforts from people from different places, and that will be my next slide. The only thing is that eventually I'll come down to this thing. I mean, when the whole attention was to solve the problem of how to generate the masses, only one person somehow mentioned about the other boson of the Goldstone. I mean, Goldstone's other scalar. I mean, so eventually, I mean, we will see that this scalar is our Higgs scalar that we found in 2012. And it has, I mean, in the beginning, I mean, its importance was not realized and nobody paid. I mean, it was not at all a serious issue to think about a massless, a chargeless spin zero particle. I mean, that was not needed. Now I come to the next slide, which is a kind of a summary of who did what. So everybody was thinking about the mass generation mechanism. Now, as I mentioned, what Anderson did was that he speculated that in a non-relativistic plasma, maybe photon. It's because of the so in a non-relativistic plasma inside a superconductor, because of the Meissner effect, the magnetic fields are repelled. Now, the fact that electromagnetic field is not long ranged, that it is confined maybe on the surface, implies that photon is massive, because the short range nature of the force implies the corresponding gauge boson is massive. Okay, so he speculated that could be it is due to marrying the masslessness Goldstone boson arising from spontaneous symmetry breaking associated with the Cooper pair formation. With the Cooper pairs are not the Goldstones, by the way. With the masslessness of the photon, he speculated that, and that's how the embarrassing massless boson can be avoided. The embarrassing massless boson, because your global symmetry is spontaneously broken, that could be avoided in a non-relativistic plasma. Then there are two guys, one is Klein, the other is Ben Lee. It is not T.D. Lee, Ben Lee. So they demonstrated that the Goldstone theorem tells you that whenever there is a spontaneous breaking of a global symmetry, there will be massless bosons. So Goldstone theorem fails in non-relativistic theories. Okay, which means that in a non-relativistic theory, you don't have to bother. That's what Klein and Lee emphasized. But they also said that their proof can be generalized to also relativistic theories. Okay, so then entered this person Gilbert, who was a student of Nick Kemmer in Cambridge, but then in the early 50s. But Nick Kemmer moved to some other place, maybe Edinburgh, and then he joined Salam. So Gilbert was Salam's student. Then Gilbert was working alone, I mean, not with Salam. And then he demonstrated that the Klein and Lee's observation were not entirely correct, which means that in a relativistic theory, you cannot bypass Goldstone theorem, namely that the massless bosons have to be there. Okay, so it's kind of an impasse that you cannot avoid the this embarrassing situation of living with a massless boson, a scalar boson, in relativistic theories. Okay. Now let me tell you about Gilbert. So he wrote. I mean, this paper was definitely one of the most influential papers of that time, and subsequently the set of people, including Peter Higgs, who found the caveat that it's not that Gilbert was wrong, but some of the loopholes were unaddressed. I mean, that was what the rest of the people found. So Gilbert didn't consider the existence of gauge fields in his theory. That was the loophole. That it's not that Gilbert was wrong. Let me emphasize. I mean, it is that, I mean, this particular aspect, that what happens in the presence of gauge bosons, was not addressed by Gilbert. But that was the last paper Gilbert wrote in particle physics. I mean, when he was working in these aspects, he became friendly with Watson, who was working with Crick. And after PhD, when Gilbert moved to Harvard for his postdoc, he was so fascinated by the work that Watson and Crick were carrying out that Gilbert moved to a completely different area, namely, biology or the molecular dynamics of biophysics. And in 1980, he got Nobel Prize in chemistry for his, for discovering the molecular structure of DNA. And he is one of the father figures, he was, of Human Genome Project. Now think of Peter Higgs. So Gilbert was a particle physicist. He made that influential contribution in the contemporary, one of the most, probably the most important area of particle physics at that time, and then moved to some other area, namely whatever you call it, chemistry or molecular or biology, and he got Nobel Prize there. Now Peter Higgs was doing his master's in biophysics in UK. I forgot, I mean, which university, maybe in Edinburgh. And then he was increasingly getting interested in particle physics. Okay, so their paths sort of crossed that way. I mean, now these guys, I mean, Braut, American guy, and Englert is from Belgium. See, they were mostly motivated. See, their background was mostly what you can call it a consumer perspective. I mean, nowadays they're very diverse. I mean, if you talk to a consumer person or a high energy person, I mean, often they don't understand, they can't communicate in the same field theoretic language. Maybe they're, even though, I mean, both are doing field theory, everything. But in those days, I mean, which is kind of the infancy of what you traditionally call, what would be traditionally known as consumer physics, and what would eventually, go as a separate branch of high energy physics. I mean, they are intimately, inextricably connected. And so Braut and Englert were actually studying the spin waves and the Goldstone bosons associated with the spin wave properties. Although their 1964 PRL paper, for which Englert got Nobel Prize, doesn't contain the context of spin waves, but they elevated actually Anderson's assertion that it is possible to construct a gauge invariant theory of photon. Means photon is massive and the theory is gauge invariant, and the massless scalar boson disappears and reappears as a longitudinal component. Okay, so they start with there is a massless boson, but that contributes to the longitudinal degree of freedom. So, and they could explain that how photon becomes massive. I mean, that was the the need of the day at that time. They all concentrated how to make a massive photon, because they have to explain beta decay, where you need a massive well, in those days it was not called W, but a massive charged boson. Then in Imperial College, Guralnik Guralnik was a student of Gilbert. Guralnik and Hagen, together with Tom Kibble, you see that they were working probably in the same corridor as Salam and Ward, but none of them was talking to the other group. I mean, this group was not talking to the other group. So they were interested in the symmetry breaking properties, and they emphasized that the Nambu-Goldstone boson did not be present in locally conserved theories. And the force carrier, I mean, force carrier means a photon-like force carrier, like the W boson in beta decay. It could become massive by eating them up. I mean, if you read their paper, I mean, you will see that the last line of the paper is that Guralnik thanked Salam for hospitality. But I'm pretty sure they didn't talk to each other, because at that time, Salam and Ward, they were the world expert of renormalization. They were the experts of the Young-Mills theory. They were trying to unify weak interaction with electromagnetism. They had no clue at that time of how to make the W boson and the so-called Z boson at that time massive. But they were probably working in the same corridor. And these guys were not concerned with Young-Mills theory. Young-Mills theory was not a popular theory in many parts of the world. So nobody put them, make them talk to each other. Nobody put the 2 and 2 together and make it 4. So these guys, wrote something what Brout and Englert also wrote a couple of months later, that the Goldstone bosons, the massless scalar bosons, need not be present in a locally conserved theory, and W boson becomes massive. So they could solve this problem together with Brout and Englert, that there is that the presence of the massless Goldstone boson is actually not a curse; it is a boon, that it could solve the other curse, namely that of a massive photon, charged photon, which we encountered in beta decay, in weak interaction. Okay. Now, what did Peter Higgs do? Peter Higgs did something very profound. He wrote something very similar in the line of what Brout and Englert and what Guralnik, Hagen, and Kibble wrote, namely how to solve the problem of mass generation by showing that Gilbert's argument that the presence of the Goldstone boson cannot be avoided in. Are you with me? Are you listening? Hello.
Yeah. Yes. Yeah.
Oh,
Yes.
okay,
Yes.
okay, fine.
Yes. Yes.
Sometimes I don't know. I mean, whether I'm switched off or not. Like, okay,
No,
fine. Yeah.
it's
So whether
fine.
So whether Higgs sort of found the loophole in Gilbert's argument. Gilbert's argument was, let me remind you, Gilbert's argument was that there is a roadblock, namely in a relativistic theory, there has to be massless Goldstone boson, and since massless Goldstone boson is not favored by nature, so you have a roadblock. Now, there is no. It is mathematically correct, and also it is correct. You cannot avoid it. But what Higgs showed is that if you have gauge field in your theory, then that massless Goldstone boson is eaten up, exactly what Brout and Englert or Guralnik, Hagen showed. Kibble's presence was very important in providing the group theoretic argument. So everything was falling in place. So Higgs showed that you can solve the problem of that Gilbert pointed out. The impulse can be lifted, namely you have an explanation of the massive gauge boson. But when he sent this paper, so this is what in one of the techniques that Brent Key mentioned. Brent Key was the leader of theory division once, at that time in mid 60s. And of course, they remain active. They used to come to, certain events, till the time they could walk. So Prentke was a regular presence. So Prentke mentioned that when he got this paper, he had the habit of, even subsequent leaders of theory division who became editors of PLB, they used to distribute the papers for referring to the colleagues, to the people in the same corridor. So Prentke also, so when Higgs sent his paper to PLB, Prentke sent this to some of his colleagues, and they said that this paper can be should be sent to Nuovo Cimento. Now, a detailed version of the paper. So he wrote two papers. First is the mechanism of mass generation, and there was another paper, and with some pointed details. Now, the second paper was rejected by PLB, and the recommendation of the editor, Prentke, was that you send it to Nuovo Cimento. But in those days, Nuovo Cimento was not refereed journal. So Higgs thought that, okay, let me then send it to PRL. So he sent it to PRL instead of sending it to Nuovo Cimento. Now the PRL editor sent it to a referee, and this is something I heard, I don't remember from whom, that the referee was Nambu. Now he pointed out what happens to the other scalar. The sigma I was referring to, the radial excitation. What happens to that? Now you have to give some, some comments on the implications of that sigma. Even though, you don't have to give the full phenomenology or whatever. So very quickly, Higgs, whose main intention, like everybody else, was to explain the mass generation mechanism, had to write something to the effect of, justifying the presence of a chargeless neutral scalar. Something completely esoteric. There was no need or no, no evidence for that. In those days, it was very difficult to add a new particle, like, unlike what we do these days. So he wrote something to that effect and sent it back to PRL. And of course, the paper got published after that. So the paper got published not because of that sigma, but because, that was what was added because of referees' comments. But primarily, the goal was to explain the mass generation mechanism. So all the papers, like Braut and Englert paper, Goralnik, Hagen-Keppel paper, and Peter Higgs, all got published in 1964 in PRL. But only Peter Higgs talked about the behavior, even though sketchily, of the Goldstone's other scalar, which is massive. Okay. Now, roll back a few years, in the late 1950s, probably 57 or 58, Glashow constructed a model. Now, there was the other problem I was telling you, that there was a speculation that the theory of beta decay and theory of photon might have a common link. Because as I told you, if you extend the theory of electron to a pair of electrons, or for example, neutron and proton, you get more than one carrier and a charged carrier. Okay, if proton is charged, there has to be a charged carrier which can take a neutron to a proton. So Glashow constructed a model with a massive triplet gauge bosons. I don't think it was I don't remember now whether it was the same notation, but Salam actually put X for Z, but I don't remember what was Glashow's notation. But anyway, nowadays we know as W plus minus and Z, together with a massless QED photon. And of course, he just put the masses by hand, so it was not renormalizable. He only hinted that the unification of weak and electromagnetic forces might contain the clue for renormalizability. But of course, if you have a massive gauge boson put in by hand, there is no renormalizability. Then Salam and Ward, I mean, they were the world expert of renormalization, and they were independently constructing this SU2 cross U1 theory, but they were unable to digest the masses of the W and Z bosons. I mean, that sort of bothered them, okay? Now, Kibble incorporated the group theoretic idea into spontaneous symmetry breaking. As I told you, these 2 degrees of freedom from the transverse degrees of freedom of the massless gauge boson and the 2 degrees of the real and the imaginary part of the scalar boson was redistributed in the form of the longitudinal mode of the gauge boson, and that particular scalar radial direction, which is massive. I mean, that is the direction for which Peter Higgs was forced to put some comments by the referee. Now, of course, eventually Weinberg used this spontaneous symmetry breaking idea in the SU2 cross U1 model that was kind of, I mean, everybody stands on the previous guy. So that was the most complete model that it contains everything. Okay, the SU2 cross U1 model with the idea of spontaneous symmetry breaking, how the massless boson reappears in the form of the longitudinal degree of freedom of a massive gauge boson. Now, Salam independently promoted the SU2 cross U1 model, realizing the significance of this mass generation mechanism, which maintained gauge invariance. Eventually, I don't have the time, but if I ever have any time to talk about, that was another, kind of interesting, it's like a detective story, how 't Hooft realized the importance of this real massive scalar. It is the sigma, which could play a decisive role in making it renormalizable. I mean, by keeping the model safe from very bad, ugly, high energy behavior. Okay. Finally, in 2012, CMS and Atlas saw the other scalar of the Goldstone, namely the Higgs boson. And eventually, when the Higgs coupling to the 2 gauge bosons, namely ZZH interaction strength, was found to be consistent with the Z mass, the coupling strength has to do with the Z mass. The mass generation mechanism was proved. You see that before that, you found the Z boson mass measured with the precision of 1 in 10 to the 5, but the mass generation mechanism that everybody was talking about was not experimentally proved till the time the associated sigma, namely in this case the Higgs boson, I'm talking about H in a different notation, whose strength to the 2 gauge boson was found to be consistent with the mass, with the order parameter, in fact, of the Z boson. And this proves the mass generation mechanism, and this mass generation mechanism was predicted by all these people, Anderson, Braut, E for Englert, Guralnik, Hagen, Higgs, K for whom?
Kibble.
Kibble and 't Hooft. Exactly. Now, eventually, the disintegration of this particle into 2 photons and the study of angular momentum confirmed its spin 0 nature, right? I mean, because a spin 1 particle cannot decay into 2 spin 1 particles. Young's theorem, a spin 1 cannot decay to 2 spin 1. So the fact that the Higgs particle was found to decay into 2 photons was a proof that it has spin 0. Whether it has positive parity, I mean, whether it is even or odd, means CP even or CP odd experimentally. I mean, just in the standard model, you cannot produce a CP odd particle. But experimentally, to prove it, you need to see the angular distribution properties, and a pure CP odd is disfavored, but a mixture could still be allowed in some accuracy. In some percentage, but normally we tend to believe that the standard model is valid and correct, and it is a positive parity spin 0. Spin 0 is already proved. The Higgs boson that was predicted by Weinberg, Salam, Glasgow model. Now, what is so good is that that people tend to overlook is that this is the first time. I mean, if Higgs happens to be an elementary particle, the Yukawa force has been measured for the first time. I mean, so LHC, so gauge force has been measured previously, but it's the Ikawa force that has been measured in the context of Higgs decaying into two fermions if Higgs happens to be an elementary particle. The reason I'm telling you so, because although the notion of Ikawa interaction was known, but Ikawa mesons were known, but they were all artifacts of strong interaction. The question is, I mean, it is not yet ruled out whether the Higgs boson we have seen is an artifact of some other strong interactions at a high energy scale. I might, in the last slide, the next slide is my last slide. I mean, very briefly talk about, I'll not talk about and just hint about it. But if it is the elementary particle, Yukawa force has been measured in a very good precision at LHC. And unlike electromagnetic weak and strong forces, I mean, this Yukawa interaction strength is not quantized. I mean, it can be anything. So the standard model of Glashow, Weinberg, and Salam is now a standard theory. It is not, shouldn't be called a model. It's a standard theory. The mass of the Higgs boson is approximately 125 GeV with an error of about 1 GeV. This is within the range predicted by precision studies of the weak force carriers. Okay, I mean, I did my PhD in precision calculation many years ago, but eventually, the level of precision by the experiment and the experiment was lab experiment, but the theoretical calculations became increasingly, improved further and further. The question is, that people who are, engaged in beyond the standard model physics think that how to tame the ugly quantum mechanical behavior, why the Higgs boson mass is like 100 GeV, why it is not like 10 to the 15 or 16 GeV, as heavy as the scale where you can extrapolate your standard theory. Now, whether it is supersymmetry that will explain you or extra dimension, well, I mean, supersymmetry is also kind of an extra dimension in fermionic coordinates. So I don't want to differentiate. Well, I mean, in a different sense, of course. I mean, extra dimension is extra space-like dimension curl, but supersymmetry could be thought of an extra dimension in fermionic coordinates. Or there are one Higgs or more Higgses. And the last line is something that I worked with my last student who has now completed and left for postdoc, whether Higgs is elementary or the Higgs mechanism or the forces that have been measured is an artifact of some strong interaction unexplored and at a TeV or at a much higher scale. So what we see today as Higgs, whether it is a what should I say, a Goldstone boson, but I mean, where there is a little bit of symmetry breaking made it massive, like 125 GeV. So it is one of the explanations of why its mass is not very high. I mean, it is this naturalness problem that has filled our mind. I mean, we are uncomfortable with this ugly quantum mechanical behavior. Could be explained either by supersymmetry or extra dimension, or the fact that the Higgs we have seen is not elementary, but maybe a composite object, an artifact of some unknown strong interaction. Okay, thank you very much. I took some extra minutes. Maybe I tried to bit more explicit in explaining things. Sorry for taking this extra time. Thank you very much.
Okay. So thank you. For this very nice, story. And sorry about this interruption. Okay, which happened because of some technical reasons. Okay. So now floor is now open for questions. Anybody who wishes to ask any question, please feel free.
Nobody asking, can I ask a question?
Sure.
Okay. I just feel curious. I understand the mindset was different at that time, but sigma being there in equations, there are two possibilities. Either people just somehow ignored it because they had a different focus, or they thought that it is some mathematical artifact like a superficial degree of freedom? Any indication that what happened? Ignored it or considered it mathematical artifact?
Well, I mean, the way it is written today was not the way it was written in those days. I mean, people were only interested in the Goldstone bosons, which was creating the problem. And in fact, I mean, you might have, I don't know, there was an interview of Higgs, that why, I mean, what made you look for that, what others didn't look at. And he confessed that none of us was looking at the other things.
It was Nambu.
It was Nambu who sort of prompted him. So,
okay. And one more question which I wanted to ask is that this issue of the issue of charged massless particle, which was there, but people wanted to make it massive.
The massive, it has to be massive because otherwise you cannot explain the short range nature of the.
No, I understand. But if confinement was, confinement occurred later.
Yes.
If confinement was known at that time, people would have probably attempted that option also.
Yeah.
Because we know that gluons are massless, but there is a short range interaction.
Exactly.
Confinement.
No, absolutely. I mean, in fact, I mean, we had to wait till 70s?
70s, right.
70s,
right.
Yeah, for that, yeah.
There would have been different direction to explore at that time, which would have been wrong, which actually would have been wrong, right?
Exactly.
Right.
Just 20 years earlier.
Okay. Okay, thank you. Yes.
Okay. So any other question? So let me just ask you. So I mean, would you say that in this paper of Broud and Englert, because they also got this Nobel Prize, the discussion of this extra scalar as a real particle was explicit enough?
No, it was not there. It is not there. Okay. Did you? I mean, you can look at the 1964 PRL. It is not there.
So why, I mean, they got Nobel Prize but not Kibble and Guralnik, because in both cases they were talking about, they were focusing on that some particle becomes massive, but this extra scalar which existed, I mean.
You see that, first of all, I mean, there is I don't know, was there a third person in the list or there were only two?
No, there were only two because Broud was dead.
Broud was dead by that time. It has to do also with the timing also, although the reason was not very explicit why this set and not the other guys. But you have to see, I mean, the timing of, I mean, I think there are several months apart. I mean, I don't exactly know the reason, but if you read the paper of Broud and Englert, and read the paper of Hagen, Kibble, and is the other guy, Guralnik. They are pretty similar, except the Kibble paper is, I mean, you read it more easily. I mean, there are more, group theoretically, it is more profound. You will see the way symmetry breaking has been discussed and so on. But it's basically I couldn't see much of a difference between the ultimate conclusions, and the ultimate conclusion is that, I mean, you can explain a massive gauge boson in a gauge invariant theory. I mean, that was the ultimate conclusion, and the same conclusion in Peter Hicks's paper, except for the that mention about the real excitation.
Yeah. So I mean, so what exactly? Why exactly? I mean, Englert won, but not this Kibble group. We don't know. Is it?
Actually, maybe there are some reasons, but I mean, I don't have that insight to decipher between there. I didn't think much beyond that. I mean, what I told you.
Okay, sure. Okay.
I'm sorry I took a long time, but I
didn't. That's all right.
Giving the explanation. I mean, yeah.
No, that's all right. Actually, explanations are always needed. A lot of students are there, and also, stories are always interesting, rather than technical things. Okay. So, anybody else, please feel free. Okay. Yeah. So I think then I would like to thank Professor Bhattacharya for a very interesting talk. And I think knowing history is always, good for everybody. We know what transpired, why our models are the way they are nowadays. So history is always, very interesting to know. And so I would like to thank him again. And I don't know if Suresh is there. Okay. And Tapo, are you there? Okay. Okay. So I think. Okay. So I think then, if there are no further questions, let me thank finally, and then I think we are going to close. Let me thank then all the speakers on behalf of the organizing committee. Our speakers, Professor Bhattacharya. Then in the morning we had two speakers also, and so thank you all for making our this celebration of Foundation Day, more enjoyable and more useful to the IOP community at large.
I wish you all the best on this occasion. I mean,
Thank you
all
very
the
much.
IOP family, all
Thank
the.
you.
Thank you, Professor Bhattacharya. Yes.
Okay. So thank you, Brother Bhattacharya, and thank you everybody. So I think we are going to close this technical session. Thank you all.
Bye-bye.
Bye-bye.
Bye, Professor Bhattacharya. Bye.
Bye-bye.